Imagine for a moment that the universe isn't what we think it is. Picture all the galaxies, stars, and clusters of matter moving in harmony, each governed by the known laws of physics. But then, something strange interrupts this picture. Something massive, invisible, and completely unexplainable. Galaxy clusters, some of the largest structures in existence, are all moving toward an unseen point in the cosmos. They're not drifting randomly, but instead being pulled by a force we cannot fully understand. Scientists call it dark flow. And it might just be one of the biggest unsolved mysteries in the universe. What could be out there, far beyond what we can observe? Could it be a colossal structure so large that it dwarfs our known universe? Or is it evidence of an entirely different realm of existence, hidden from our view? The more we look into this phenomenon, the more baffling it becomes. The idea of dark flow shakes the foundation of what we think we know about the cosmos, and the answers may lie beyond the limits of human comprehension, or, perhaps, they're just waiting for us to uncover them. To understand dark flow, let's first consider the universe as we know it. In the observable universe, everything we see, from the smallest asteroid to the largest galaxy, is bound by physical laws. These laws dictate how objects move, interact, and influence one another. One of the key principles is the idea that the motion of galaxies and galaxy clusters should be fairly random, dictated only by gravitational interactions between them. But when astronomers started looking closely, they discovered something unusual. A large number of galaxy clusters were all heading in the same direction, as though being pulled by an enormous, unseen force. This motion isn't small. We're talking about speeds of over 1,000 kilometers per second. That's faster than anything you'd expect from typical gravitational interactions. And what's even stranger? This movement seems to be pointing toward a region of the universe that we can't even see. It's happening beyond the observable universe, the part of space that light has had time to reach us from since the Big Bang. The discovery of dark flow began in the late 2000s, when researchers studying data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, noticed something peculiar in the cosmic microwave background radiation, or CMB. The CMB is essentially the afterglow of the Big Bang, a faint echo of the universe's birth. Scientists use it as a kind of cosmic map to measure the motion of distant objects. When analyzing the CMB, they found a consistent pattern indicating that galaxy clusters were moving toward a specific region of the sky, a motion that couldn't be explained by anything within the observable universe. The most unsettling part? This motion defies the standard cosmological model, the framework that explains how the universe works on a large scale. According to this model, the distribution of matter and energy in the universe should be fairly uniform on the largest scales. There shouldn't be anything massive enough to create this kind of pull. And yet, the evidence for dark flow is hard to ignore. What could possibly cause this phenomenon? One theory suggests that it might be the result of a structure beyond the observable universe, something so massive that its gravitational pull is influencing galaxy clusters from billions of light-years away. This idea is both thrilling and terrifying. If such a structure exists, it could challenge everything we know about the size and scope of the universe. Another hypothesis is that dark flow might be evidence of a multiverse. Imagine if our universe is just one bubble in a vast cosmic sea, and other universes are out there, pressing against the edges of our own. The gravitational influence of these other universes could potentially explain the mysterious pull. If this is true, it would mean that the universe we see is just a tiny fraction of a much larger, more complex reality. But not everyone is convinced. Some scientists argue that the evidence for dark flow could be a statistical fluke or an artifact of how the data was analyzed. Others think it might be caused by something we don't yet understand about the physics of our own universe. For instance, it's possible that dark flow is related to dark energy or dark matter, two other mysterious components of the cosmos that we've only begun to study. Despite the skepticism, the mystery of dark flow remains one of the most intriguing puzzles in astrophysics. It forces us to confront questions about the nature of the universe and our place within it. Is the observable universe just a tiny island in an infinite sea? Are there other forces, dimensions, or realms shaping the cosmos in ways we can't yet perceive? The search for answers continues, with new data from telescopes and satellites helping to refine our understanding. Some scientists believe that future observations will provide more clarity. Projects like the James Webb Space Telescope and next-generation cosmic surveys are expected to reveal more about the universe's structure and behavior. But even as we gather more data, the question of dark flow might remain unanswered for a long time. It's a mystery that challenges not only our scientific knowledge but also our imagination. Think about it. If dark flow is real, it suggests that there's something out there, beyond the reach of our telescopes, influencing the motion of some of the largest structures in the universe. It's a reminder that the cosmos is far more complex and mysterious than we can currently comprehend. For all our advancements in science and technology, there's still so much we don't know. As you let that idea sink in, consider this: what if dark flow isn't an anomaly at all, but rather a clue, a hint pointing us toward a deeper understanding of the universe? What if it's the first piece of a puzzle that will eventually reveal an entirely new framework for thinking about space, time, and reality itself? The story of dark flow is still unfolding, and its implications are staggering. It's a phenomenon that invites us to look beyond the limits of our knowledge and consider possibilities that are as vast and infinite as the universe itself. If we take a moment to truly grasp what dark flow implies, it becomes clear that this mystery isn't just about galaxy clusters moving toward an unknown point. It's about the boundaries of human knowledge and the tantalizing possibility that something greater exists beyond our cosmic horizon. The very concept forces us to rethink the framework of the observable universe, the notion of space-time, and the role of unseen forces shaping the cosmos. To explore dark flow further, we need to dig deeper into its potential origins. One of the most popular theories ties the phenomenon to what physicists call the inflationary model of the universe. According to this model, the universe expanded exponentially in the moments following the Big Bang, stretching space-time to unimaginable proportions. During this rapid inflation, quantum fluctuations in the very fabric of space could have created density variations. These variations might have led to the formation of structures outside our observable universe, structures so massive that their gravitational influence extends into the regions we can observe today. This brings us to a crucial question: what lies beyond the observable universe? The observable universe is essentially a sphere centered on Earth, limited by the speed of light and the age of the universe. Beyond this horizon, there may be regions of space we'll never see, even if we wait billions of years. Yet these hidden regions could still impact the parts of the cosmos we can observe. If there are enormous concentrations of mass, like superclusters or even more exotic structures, they might be the cause of dark flow. Another compelling explanation for dark flow is rooted in the idea of cosmic strings, theoretical, ultra-thin, and incredibly dense remnants of the early universe. Cosmic strings are thought to form as the universe cools from its initial state of extreme energy. If they exist, these strings could stretch across vast distances, their immense gravitational pull subtly influencing the motion of galaxies. Although cosmic strings remain hypothetical, they offer an intriguing possibility for explaining the mysterious motion of galaxy clusters. Now let's delve into the more speculative ideas, which often capture the imagination of scientists and the public alike. One of these is the multiverse hypothesis, which suggests that our universe is just one of many. If other universes exist, their gravitational fields might interact with our own in ways that manifest as phenomena like dark flow. Imagine neighboring universes exerting a subtle but persistent pull on certain parts of our cosmos. While this idea might sound far-fetched, it's supported by some interpretations of string theory and quantum mechanics. But what if the cause of dark flow isn't an external structure or a neighboring universe? What if it's something inherent to the fabric of spacetime itself? Some scientists propose that dark flow could be tied to topological defects, irregularities in the structure of spacetime that emerged during the universe's formation. These defects could act like cosmic potholes, influencing the motion of nearby matter. If this is the case, studying dark flow might provide insight into the universe's earliest moments and the processes that shaped it. As intriguing as these theories are, they all face a common challenge: the lack of direct evidence. Observing the effects of dark flow is difficult enough. pinpointing its cause is even harder. Part of the problem is that we can only see so far. The observable universe represents just a tiny fraction of the total cosmos, and the forces driving dark flow might be coming from regions we'll never be able to observe. Despite these limitations, scientists are using every tool at their disposal to investigate this mystery. For example, data from the Planck satellite, which succeeded WMAP in mapping the cosmic microwave background, has been used to refine our understanding of dark flow. Although the results are inconclusive, they hint at patterns that might support the existence of this large-scale motion. Another promising avenue of research involves studying the distribution and motion of galaxy clusters in even greater detail. Advances in telescope technology, like those offered by the Vera C. Rubin Observatory and other next-generation facilities, will allow astronomers to map the universe with unprecedented precision. By analyzing the movements of thousands of galaxy clusters, scientists hope to uncover more clues about the nature of dark flow and its possible sources. The search for answers isn't just about solving a cosmic puzzle, it's about pushing the boundaries of human knowledge. Dark flow represents a frontier, a place where our current understanding of the universe breaks down. It's a reminder that science is a journey, not a destination. For every mystery we solve, new questions emerge, each more profound than the last. And yet, the implications of dark flow go beyond science. They touch on some of the deepest philosophical questions humanity has ever asked. What is the true nature of reality? Are we part of a larger cosmic structure we can't perceive? Could there be other universes with their own laws of physics, their own galaxies, their own stars? Dark flow challenges us to think about these questions in ways that are both humbling and exhilarating. For now, dark flow remains an enigma, a riddle written across the heavens. But one thing is certain, its discovery has opened a door to new possibilities, new theories, and new ways of thinking about the universe. It's a phenomenon that reminds us of the vastness of the cosmos and the limits of our understanding, a reminder that, no matter how much we learn, there will always be more to discover. The mystery of dark flow doesn't just push the boundaries of science, it forces us to confront the limitations of our perception. What if the cosmos we observe is just a small fragment of a much larger, unfathomable reality? Dark flow is a tantalizing glimpse of what could lie beyond the edges of the observable universe, a frontier so distant that even the fastest signals in the universe, traveling at the speed of light, will never reach us. To better understand why dark flow has captured the attention of scientists and theorists alike, let's explore its deeper implications. In the standard cosmological model, the universe is homogeneous and isotropic on large scales, meaning it looks roughly the same no matter where you observe it. This assumption is the foundation for much of modern astrophysics. The discovery of dark flow, however, challenges this assumption. If large-scale motion exists that cannot be explained by the distribution of matter within the observable universe, then the universe might not be as uniform as we once thought. This inconsistency raises another intriguing question. Could there be a boundary to the observable universe, a kind of edge beyond which reality behaves differently? Some physicists speculate that this boundary might not just be a limitation of what we can see but a transition into a completely different type of spacetime. If so, the forces driving dark flow could originate from a region of the cosmos where the laws of physics themselves are unlike anything we've encountered. Another aspect to consider is how dark flow fits into the broader context of cosmic mysteries. The universe is already filled with phenomena we don't fully understand, from dark matter and dark energy to the very nature of black holes. Dark flow adds another layer to this puzzle, hinting that the cosmos might be governed by forces and structures we haven't even begun to identify. This could mean that our current understanding of gravity, space, and time is incomplete, or even fundamentally flawed. One potential avenue for exploring these possibilities is through the study of gravitational waves, ripples in the fabric of spacetime caused by massive cosmic events. Gravitational wave detectors, like LIGO and Virgo, have already revolutionized our understanding of the universe by confirming the existence of black hole mergers and neutron-star collisions. Some theorists suggest that gravitational waves could also provide indirect evidence of large-scale structures beyond the observable universe, potentially shedding light on the cause of dark flow. If dark flow is connected to the influence of massive structures beyond our cosmic horizon, then detecting these effects through gravitational waves or other subtle distortions in spacetime could be a game-changer. This type of research could reveal whether the forces driving dark flow are tied to previously unknown aspects of our universe, or to something even more exotic. Let's shift our focus to another fascinating idea: the possibility that dark flow is evidence of an anisotropic universe. In simple terms, this means the universe might have a preferred direction, a kind of cosmic flow that extends across the largest scales. This idea is at odds with the principle of isotropy but could explain why galaxy clusters appear to be moving in the same direction. An anisotropic universe would fundamentally reshape our understanding of the cosmos, suggesting that the early universe's conditions left behind large-scale imprints still observable today. The concept of a preferred direction ties closely to theories about the universe's initial conditions. During the first moments after the Big Bang, the universe was in an incredibly hot and dense state, expanding rapidly in what's known as cosmic inflation. If inflation wasn't perfectly uniform, if certain regions expanded slightly faster or slower, this could create the kind of large-scale flows we now observe as dark flow. In this sense, dark flow might be a fossil imprint of the universe's earliest moments, offering a rare glimpse into its birth. But what if dark flow isn't just a relic of the past? Some researchers propose that it could be an active process, an ongoing interaction between our universe and something else. This brings us back to the tantalizing idea of the multiverse. If other universes exist and are exerting gravitational influence on ours, dark flow might be the first observable evidence of these interactions. This idea is particularly appealing because it connects dark flow to broader questions about the nature of reality and the potential existence of parallel worlds. The multiverse theory isn't without its challenges. One major issue is that it's incredibly difficult to test. By definition, other universes would lie outside our observable realm, making direct observation nearly impossible. However, indirect evidence, such as unexplained motions like dark flow, could provide tantalizing hints. If the multiverse is real, it could explain not only dark flow but also other cosmic anomalies, like the uneven distribution of galaxies or the mysterious nature of dark energy. As we continue to explore these possibilities, it's important to remember that science thrives on uncertainty. The questions raised by dark flow are exactly what drive progress, forcing us to refine our theories, develop new tools, and challenge our assumptions. The search for answers might take decades, or even centuries, but the journey is just as important as the destination. Imagine a future where humanity has the tools to directly observe regions of space far beyond the current limits of the observable universe. Advanced telescopes, faster-than-light communication technologies, or even new breakthroughs in physics could one day allow us to peer into the regions driving dark flow. What might we find? Could it be a colossal structure, a neighboring universe, or something so alien that it defies all comprehension? For now, dark flow remains an open question, a cosmic enigma that beckons us to look deeper, think harder, and dream bigger. It's a reminder that the universe is vast, mysterious, and full of surprises. The forces shaping the cosmos are far greater than we can imagine, and our journey to understand them is just beginning. If we follow this thread further, we're drawn into an even more profound realization. The universe we see, study, and model might be just a fragment of a much larger and more complex reality. Dark flow serves as a doorway to the unknown, urging us to ponder questions that may have no clear answers. Yet, these questions, however elusive, are what make this mystery so exhilarating. To fully appreciate the scale of dark flow, it's worth considering just how vast the affected regions are. When we talk about galaxy clusters, we're referring to some of the most massive structures in the universe, containing thousands of galaxies bound together by gravity. These clusters span millions of light years and are themselves part of even larger structures, like superclusters and cosmic filaments. The fact that these colossal entities appear to be moving in unison toward an unseen point is nothing short of staggering. One way to visualize this is to imagine the universe as a vast ocean, with galaxy clusters as massive ships drifting across its surface. most of the ships move in predictable patterns, influenced by the local tides and currents, the gravitational pull of nearby structures. But then there's a subset of ships that seem to be pulled toward a point far beyond the horizon, as if guided by an invisible force. This is the essence of dark flow, a cosmic current that defies explanation, pulling entire clusters of galaxies toward an unknown destination. The question of what lies beyond the horizon is deeply tied to the concept of the cosmic light cone. Everything we observe in the universe is limited by the speed of light and the finite age of the cosmos. Light from distant regions takes billions of years to reach us, and the farther away an object is, the longer it takes for its light to arrive. This creates a spherical boundary, the observable universe, beyond which we can't see. But the universe itself is likely far larger, possibly infinite. Dark flow suggests that this unseen expanse is not empty. Rather, it's teeming with structures and forces that continue to shape the regions we can observe. Theories about these hidden regions often intersect with speculative physics. One possibility is that the source of dark flow is a great attractor, a massive concentration of matter so far away that its gravitational pull affects galaxy clusters within the observable universe. But this raises a new question: what could be so massive that it influences structures billions of light years away? Some scientists have proposed that these attractors might be primordial black holes, vast regions of dark matter, or even relics from an earlier universe. Another compelling idea is that dark flow could be a relic of higher-dimensional physics. According to some interpretations of string theory, our universe might be a three-dimensional brane embedded in a higher-dimensional space. If true, other branes might exist in this higher-dimensional space, and their gravitational influence could extend into our universe. This could explain why galaxy clusters appear to be moving toward an unseen point. It's not in our universe at all, but in a dimension beyond our perception. Of course, these ideas remain speculative. For now, they're intriguing possibilities rather than proven facts. But the beauty of science lies in its willingness to explore the unknown. Even the wildest theories can serve as stepping stones to new discoveries, pushing us closer to the truth. In recent years, researchers have begun to focus more closely on the data itself. By analyzing the cosmic microwave background (CMB), the faint afterglow of the Big Bang, scientists have identified subtle anomalies that might be linked to dark flow. The CMB is like a snapshot of the universe in its infancy, and any deviations from its expected uniformity could provide clues about the forces shaping the cosmos. While these studies are still in their early stages, they hint at a complex interplay between visible and invisible forces, a cosmic dance that might hold the key to understanding dark flow. It's also worth considering the role of dark matter and dark energy in this mystery. Together, these invisible substances make up about 95% of the universe's total mass energy content. Dark matter provides the gravitational scaffolding that holds galaxies and clusters together, while dark energy drives the accelerated expansion of the universe. Could dark flow be linked to these enigmatic components? Some researchers believe that interactions between dark matter and dark energy might create large-scale motions like those observed in galaxy clusters. Alternatively, dark flow might be evidence of something entirely new, an as yet undiscovered force or particle that operates on cosmic scales. If such a force exists, it would revolutionize our understanding of the universe, requiring a complete overhaul of the standard model of physics. This prospect is both daunting and thrilling, as it underscores the dynamic nature of science. Every discovery, no matter how small, has the potential to reshape our view of reality. Yet, for all its scientific implications, dark flow also resonates on a deeply human level. It speaks to our innate curiosity, our desire to explore the unknown, and our relentless pursuit of knowledge. The fact that we can even detect these faint motions across billions of light years is a testament to human ingenuity and determination. It's a reminder that, despite our small size in the cosmic scheme, we are capable of uncovering truths that span the entire universe. As we continue to investigate dark flow, we are likely to encounter more questions than answers. But this is not a failure, it's the essence of progress. Each new question opens a door to deeper understanding, revealing the intricacies of a cosmos that is far more complex and beautiful than we ever imagined. The journey to unravel the mystery of dark flow is far from over. In many ways, it's just beginning. But even in its unresolved state, this phenomenon has already changed the way we think about the universe. It has challenged our assumptions, expanded our horizons, and reminded us of the vastness of the unknown. And perhaps, in the end, that's what makes dark flows so captivating. It's not just a question of where the galaxy clusters are going, it's a question of where we, as a species, are headed in our quest to understand the cosmos. Dark flow is, at its core, a profound puzzle that inspires curiosity and invites speculation. The movement of galaxy clusters toward an unseen destination suggests that the universe is far more interconnected and complex than we currently understand. While our observations are limited by the boundaries of the observable universe, this anomaly teases the existence of forces and structures operating on an unfathomable scale. The question that naturally arises is this: what lies beyond the observable universe? The standard model of cosmology tells us that the universe is isotropic and homogeneous on large scales, meaning it should look roughly the same in every direction. Yet, the phenomenon of dark flow seems to contradict this principle. It suggests the presence of an asymmetry, a directional pull that defies the expectation of uniformity. This is a fundamental challenge to our understanding of the cosmos. One of the most compelling theories is that dark flow is the result of inflationary remnants, traces of the universe's rapid expansion in the moments after the Big Bang. During this inflationary period, quantum fluctuations were stretched to cosmic scales, creating the seeds for the large-scale structures we see today. Some scientists propose that these fluctuations may have interacted with neighboring bubble universes, creating gravitational imprints that persist to this day. If true, dark flow could be direct evidence of a multiverse, a collection of universes each with its own physical laws and properties. The multiverse theory, while speculative, offers an intriguing explanation for dark flow. Imagine our universe as one bubble in a vast foam of universes. If another bubble is nearby, its gravitational influence could tug on structures within our universe, creating the motion we observe as dark flow. This idea not only explains the anomaly but also expands our conception of reality, suggesting that our universe is just one small part of an unimaginably vast and diverse multiverse. However, the multiverse hypothesis is not without its challenges. For one, it is inherently difficult to test. By definition, other universes are beyond the reach of our observations, making direct evidence nearly impossible to obtain. Critics argue that while the multiverse is a fascinating idea, it may ultimately lie outside the realm of science, existing more as a philosophical concept than a testable theory. Another possible explanation for dark flow is the presence of cosmic voids, enormous regions of space that are relatively empty of matter. These voids, interspersed between galaxy clusters and superclusters, could create gravitational imbalances that drive large-scale motions. If a particularly large void exists just beyond the observable universe, it might be exerting a gravitational pull on nearby clusters, causing the directional movement we associate with dark flow. Alternatively, the cause of dark flow might be rooted in the nature of dark matter. While dark matter is invisible and interacts primarily through gravity, its distribution on cosmic scales is thought to shape the universe's structure. Some theories propose that uneven concentrations of dark matter could create gravitational anomalies, influencing the motion of galaxy clusters. If this is the case, dark flow might be a sign of previously undetected dark matter structures, offering a new avenue for research. The implications of dark flow extend beyond the scientific community, touching on philosophical and existential questions about our place in the cosmos. If the observable universe is just a small part of a much larger reality, what does that mean for our understanding of existence? Are we, as humans, limited to perceiving only a fraction of the truth? And if so, how do we reconcile this limitation with our desire for knowledge and understanding? In many ways, dark flow is a reminder of the vastness of the unknown. Despite centuries of scientific progress, there is still so much we don't understand about the universe. Each discovery, like a piece of a puzzle, reveals new mysteries to solve. This sense of wonder and curiosity is what drives science forward, pushing the boundaries of what we know and challenging us to think beyond the limits of our perception. Recent advancements in technology and observational techniques offer hope that we may one day unravel the mystery of dark flow. New telescopes, such as the James Webb Space Telescope and upcoming next-generation observatories, are designed to peer deeper into the cosmos than ever before. By studying the faintest and most distant objects, scientists hope to gather more data about the large-scale motions of galaxy clusters and the forces driving them. Another promising avenue of research is the study of gravitational waves, ripples in spacetime caused by the acceleration of massive objects. These waves, first detected in 2015, offer a new way to study the universe, complementing traditional methods like electromagnetic observations. If dark flow is linked to unseen structures or forces, gravitational waves might provide indirect evidence of their existence. Meanwhile, computer simulations are becoming increasingly sophisticated, allowing scientists to model the behavior of the universe on cosmic scales. These simulations incorporate data from observations and theoretical physics, creating virtual universes that can be analyzed and tested. By comparing these models to real-world data, researchers hope to identify patterns or anomalies that might explain dark flow. The study of dark flow also has implications for our understanding of the universe's ultimate fate. If the motion of galaxy clusters is influenced by forces beyond the observable universe, these forces could play a role in shaping the cosmos on the largest scales. This raises questions about the long-term dynamics of the universe, including its expansion, evolution, and eventual destiny. Some scientists speculate that dark flow could be a sign of an impending cosmic event, one that could alter the course of the universe itself. While this idea is highly speculative, it underscores the importance of studying large-scale phenomena like dark flow. By understanding these mysteries, we gain insight into the fundamental nature of the cosmos and our place within it. As we continue to investigate dark flow, we are reminded of the importance of keeping an open mind. Science is not a static body of knowledge but a dynamic process of discovery and exploration. Theories that once seemed far-fetched, like the existence of black holes or the accelerated expansion of the universe, are now accepted as fundamental truths. In the same way, dark flow might one day be understood as a key piece of the cosmic puzzle, a phenomenon that challenges our assumptions and expands our understanding of the universe. For now, dark flow remains one of the greatest mysteries in modern cosmology. It is a testament to the vastness and complexity of the universe, a reminder that there is still so much we don't know. But it is also a source of inspiration, driving us to look deeper, think bigger, and embrace the unknown. This relentless pursuit of understanding, the willingness to ask questions even when answers seem unattainable, is at the heart of what makes the mystery of dark flow so captivating. It encapsulates humanity's enduring quest to comprehend the cosmos, an endeavor that stretches back millennia. As our ancestors once looked to the stars with wonder, we now look deeper, aided by cutting-edge technology and the collective knowledge of generations. Yet, even as our tools grow more advanced, the universe has a way of humbling us. For every question answered, dozens more arise. Dark flow serves as a striking example of this cosmic irony. The more we study the universe, the more it reveals its hidden layers of complexity, as if inviting us to think beyond the confines of our imagination. One of the most perplexing aspects of dark flow is the apparent uniformity of this motion across vast distances. Observations suggest that galaxy clusters are moving coherently toward a region of space beyond the observable universe, seemingly unaffected by the gravitational influence of nearby structures. This coordinated movement spans billions of light-years, defying the expectations of randomness and isotropy that underpin the standard cosmological model. This uniformity implies the presence of a force or structure so massive and so far-reaching that its effects are felt across the entire observable universe. To grasp the scale of such a phenomenon is to confront the sheer enormity of the cosmos itself. It forces us to question whether our understanding of gravity, one of the fundamental forces of nature, is incomplete or flawed. Could there be an unknown aspect of gravity, something that operates differently on cosmic scales, that we have yet to uncover? Another avenue of exploration involves the concept of primordial gravitational waves. These are theoretical ripples in space-time generated during the universe's earliest moments, particularly during the inflationary epoch. If dark flow is influenced by large-scale structures beyond our observational horizon, these structures might have left imprints in the form of gravitational waves. Detecting and analyzing such waves could provide indirect evidence of the forces responsible for this mysterious motion. The cosmic microwave background (CMB), the faint afterglow of the Big Bang, also plays a crucial role in the study of dark flow. By analyzing tiny temperature fluctuations in the CMB, scientists can infer the motion of galaxy clusters relative to the background radiation. These measurements have provided some of the most compelling evidence for dark flow, revealing a consistent pattern of motion that cannot be explained by known gravitational sources within the observable universe. However, interpreting the CMB data is not without challenges. The signals associated with dark flow are subtle, often buried within the noise of other cosmic phenomena. Extracting meaningful information requires sophisticated statistical techniques and careful consideration of potential biases. Critics argue that the evidence for dark flow might be an artifact of data processing rather than a genuine cosmological signal. This skepticism underscores the need for further observations and independent verification. Future missions, such as the proposed CMB-S4 experiment, aim to provide more precise measurements of the CMB, potentially shedding new light on dark flow. These missions will be equipped with advanced detectors capable of capturing minute variations in the CMB's temperature and polarization. By comparing data from multiple independent experiments, scientists hope to confirm or refute the existence of dark flow with greater confidence. Meanwhile, the phenomenon has sparked a broader philosophical debate about the nature of scientific inquiry. How do we study phenomena that lie beyond the limits of observation? Can we develop theories that account for the unobservable, or must science remain confined to what can be directly measured? Dark flow challenges us to grapple with these questions, pushing the boundaries of what it means to understand the universe. One of the most intriguing implications of dark flow is its potential to redefine our concept of cosmic boundaries. The observable universe, limited by the speed of light and the age of the cosmos, represents only a fraction of the total universe. Beyond this horizon lies a vast expanse that we cannot see, filled with unknown structures and forces. Dark flow offers a tantalizing glimpse of this hidden reality, suggesting that our universe is shaped by influences from regions we may never directly observe. This realization is both humbling and exhilarating. It reminds us that the universe is not limited to what we can see but extends far beyond our reach. It invites us to imagine a reality that is richer and more diverse than we ever dreamed. And it challenges us to develop new tools, new theories, and new ways of thinking to explore this uncharted frontier. In many ways, dark flow embodies the spirit of scientific discovery. It is a reminder that the universe is full of surprises, waiting to be uncovered. It is a testament to the power of observation, the importance of questioning assumptions, and the value of curiosity. And it is a call to action, urging us to look beyond the familiar and embrace the unknown. As we continue to study dark flow, we are likely to encounter more questions than answers. But this is the nature of science, a never-ending journey of exploration and discovery. Each new piece of evidence, each new theory, brings us one step closer to understanding the cosmos and our place within it. And while the mystery of dark flow may never be fully solved, it will undoubtedly inspire generations of scientists and thinkers to come. The questions raised by dark flow extend beyond the realm of astrophysics and touch on the philosophical. What does it mean to understand the universe? Are there limits to human comprehension, or can the expansion of knowledge eventually unveil the ultimate truths of existence? These profound inquiries are inseparable from the scientific process, as they fuel the creativity and persistence required to confront the unknown. To better understand dark flow, let's delve deeper into the role of the inflationary model of the universe. This model proposes that during the first fractions of a second after the Big Bang, the universe underwent an unimaginably rapid expansion. This inflationary period smoothed out irregularities and distributed energy across vast expanses of space, setting the stage for the large-scale structures we see today. However, inflation could also have created pockets of the universe with varying properties, potentially accounting for structures that influence the motion of galaxy clusters beyond our observable horizon. If such structures exist, they could be remnants of pre-inflationary conditions, artifacts from an era before space-time as we know it stabilized. This raises the possibility that dark flow is a glimpse into a pre-universe, a domain governed by different physical laws or conditions. If verified, this notion could revolutionize our understanding of cosmology, introducing entirely new dimensions to our study of space and time. Theories about multiverses, the idea that our universe is just one of many, gain relevance here. If multiple universes exist, separated by boundaries or embedded within a higher dimensional framework, their gravitational effects might influence one another. Dark flow could be an observable manifestation of this interaction, hinting at the presence of a neighboring universe exerting its gravitational pull on galaxy clusters and ours. While such theories remain speculative, they offer a tantalizing explanation for the otherwise inexplicable motion associated with dark flow. The study of dark flow also intersects with the mysteries of dark matter and dark energy, two elusive components that dominate the universe's mass-energy budget. Dark matter, which interacts gravitationally but not electromagnetically, could play a role in the large-scale motion of galaxies. Similarly, dark energy, responsible for the accelerating expansion of the universe, might influence structures beyond the observable limit. Understanding how these phenomena contribute to dark flow could provide crucial insights into their nature. Moreover, the concept of topological defects, irregularities formed during the universe's early symmetry-breaking transitions, has been proposed as a potential source of dark flow. These defects, which include cosmic strings and domain walls, could exert gravitational forces across immense distances, affecting the motion of galaxy clusters. While such objects are hypothetical, their existence would profoundly impact our understanding of the universe's origins and evolution. Efforts to confirm the existence of dark flow are ongoing, with astronomers employing increasingly sophisticated methods to analyze data from galaxy surveys, gravitational lensing, and the CMB. One promising avenue is the use of redshift surveys, which measure the velocities of galaxies moving away from us due to the universe's expansion. By mapping deviations from the expected motion, researchers can identify patterns consistent with dark flow and refine their models. Critics of the dark flow hypothesis point to alternative explanations for the observed data, such as systematic errors in measurements, or the influence of local gravitational structures. For example, some suggest that the motion attributed to dark flow could result from underestimated contributions from the Great Attractor or other large-scale structures within the observable universe. These debates highlight the importance of skepticism and rigorous testing in the scientific process, ensuring that conclusions are based on robust evidence. As technology advances, the prospect of observing the unobservable edges closer to reality. Instruments like the James Webb Space Telescope and future gravitational wave detectors promise to unveil new details about the early universe and the large-scale structures that shape it. By pushing the boundaries of observation, these tools could provide definitive evidence for or against the existence of dark flow, offering unprecedented clarity about the forces that govern the cosmos. However, even as we refine our observations and theories, the mystery of dark flow reminds us of the inherent limitations of science. The observable universe is but a tiny fraction of the total cosmos, constrained by the speed of light and the finite age of the universe. Beyond this boundary lies an expanse that we can only imagine, a domain where the rules may differ and where answers to our deepest questions might forever elude us. Yet, this limitation is not a barrier but an invitation. It challenges us to think creatively, to develop new tools and frameworks for understanding the unobservable. It encourages collaboration and the cross-pollination of ideas, drawing insights from diverse disciplines to tackle the most perplexing problems. And it inspires wonder, reminding us that the universe is far more intricate and beautiful than we can comprehend. The quest to understand dark flow is more than a scientific endeavor, it is a testament to the human spirit. It reflects our insatiable curiosity, our refusal to accept the unknown as unknowable, and our determination to push the boundaries of what is possible. Whether we ultimately solve the mystery of dark flow or find ourselves faced with even deeper questions, the journey itself is a triumph, a celebration of the endless pursuit of knowledge. And so, as galaxy clusters continue their enigmatic journey toward an unseen destination, we, too, move forward, propelled by curiosity and wonder. Dark flow is a reminder that the universe is not a static entity but a dynamic, evolving tapestry of mysteries waiting to be unraveled. It is a call to action, urging us to explore, to question, and to dream of what lies beyond. The exploration of dark flow continues to fuel new ideas and push the boundaries of what we think we know about the cosmos. At its core, this mystery underscores a critical aspect of the scientific endeavor, our willingness to confront the unknown, even when it challenges the very foundations of our understanding. The idea that galaxy clusters might be influenced by a gravitational force outside the observable universe has profound implications for cosmology. To fully appreciate its significance, we must consider the observable universe's limitations. The observable universe is essentially the region of space from which light has had enough time to reach us since the Big Bang, approximately 13.8 billion years ago. This boundary, known as the cosmic horizon, isn't a fixed edge but rather a limitation imposed by the finite speed of light and the universe's age. Anything beyond this horizon remains inaccessible to us, not because it doesn't exist, but because its light hasn't had enough time to reach us. The notion of dark flow suggests that forces or structures lie beyond this horizon, influencing the motion of galaxy clusters within our observable universe. If true, it means that the cosmos is far larger, and potentially more complex, than we can directly perceive. But this idea also raises an intriguing paradox. How can we study something we cannot see? This challenge has sparked innovative approaches to understanding dark flow. One such method involves the kinematic Sunyaev-Zeldovich (KSZ) effect, which occurs when the cosmic microwave background (CMB) photons interact with hot gas and galaxy clusters. As these photons scatter off the moving gas, they experience slight changes in energy, creating detectable shifts in the CMB. By analyzing these shifts, scientists can infer the motion of galaxy clusters relative to the CMB, providing indirect evidence of dark flow. The results of such studies have been both tantalizing and contentious. Initial analyses of the KSZ effect, conducted by researchers like Alexander Kashlinsky and his team, suggested a coherent motion of galaxy clusters toward a specific point in the sky. This motion appeared to persist across vast distances, far beyond what could be explained by known gravitational sources within the observable universe. While these findings were groundbreaking, they also faced significant scrutiny, with critics arguing that the observed patterns might result from statistical noise or biases in the data. Subsequent studies have attempted to address these concerns, employing more advanced techniques and larger datasets. For instance, observations from the Planck satellite, which mapped the CMB with unprecedented precision, have provided valuable insights into the motion of galaxy clusters. While some analyses have supported the existence of dark flow, others have found no significant evidence for it, leaving the scientific community divided on the issue. This ongoing debate highlights the importance of skepticism and rigor in scientific inquiry. The case for dark flow remains unproven, and alternative explanations must be thoroughly considered. For example, some researchers propose that the observed motion of galaxy clusters could result from local gravitational influences, such as the Great Attractor or other large-scale structures within the observable universe. Others suggest that the evidence for dark flow might be an artifact of the methods used to analyze the data, emphasizing the need for independent verification. At the same time, the study of dark flow has broader implications for our understanding of the universe's structure and evolution. If the phenomenon is real, it could provide critical insights into the nature of cosmic inflation, the mysterious force that drove the universe's rapid expansion in its earliest moments. Inflation is thought to have created vast regions of space that are causally disconnected from our own, leading to the possibility of structures and forces beyond our observational reach. Dark flow might be a direct consequence of these hidden regions, offering a rare glimpse into the universe's larger framework. Another compelling avenue of exploration involves the potential role of exotic physics in explaining dark flow. The Standard Model of Cosmology, based on Einstein's general relativity, provides a remarkably successful description of the universe on large scales. However, it is not without limitations. Phenomena like dark matter, dark energy, and now potentially dark flow suggest that our understanding of gravity and other fundamental forces may be incomplete. Theories such as modified gravity or higher dimensional models could offer alternative explanations for the motion of galaxy clusters, challenging the conventional framework of cosmology. The possibility of higher dimensions is particularly intriguing. Some theories, such as string theory and brainworld cosmology, propose that our universe exists as a brane within a higher dimensional space. If true, interactions between our brane and other, unseen dimensions could influence the motion of galaxy clusters, creating effects like dark flow. While such ideas remain speculative, they open up exciting possibilities for understanding the universe's underlying structure. The search for answers continues to inspire new technological advancements. Future missions, such as the proposed Lynx X-ray Observatory and next-generation gravitational wave detectors, promise to provide more detailed observations of galaxy clusters and their motion. These instruments could help resolve lingering questions about dark flow, offering new perspectives on the forces shaping our universe. As we await these breakthroughs, the mystery of dark flow remains a powerful reminder of the cosmos's boundless complexity. It challenges us to confront the limits of our knowledge and to think creatively about the possibilities that lie beyond. Whether or not we ultimately solve this enigma, the pursuit of understanding is itself a testament to humanity's enduring curiosity and ingenuity. In the grand scheme of things, dark flow is but one chapter in the larger story of our quest to comprehend the universe. It invites us to embrace the unknown, to ask bold questions, and to imagine what lies beyond the horizon of our current understanding. And in doing so, it reminds us that the true beauty of science lies not just in the answers it provides, but in the mysteries it reveals. The mysteries surrounding dark flow force us to confront one of the most profound questions in science: how much of the universe is truly knowable? As it stands, the observable universe is just a sliver of the cosmos, a vast, incomprehensible expanse where laws, conditions, and even realities may differ radically from what we understand. The sheer scale of the forces potentially driving dark flow is staggering. Imagine a gravitational source so vast and so distant that its effects can be detected across billions of light years, tugging at entire galaxy clusters. If such a structure exists, it would redefine our understanding of cosmic formation, hinting at unseen dimensions of the universe's past. Could it be a remnant of the Big Bang's earliest moments, where chaotic conditions forged gravitational anomalies? Or does it signal the presence of regions of space shaped by entirely different physical principles? One possibility is that dark flow is a relic from the pre-Big Bang era, a concept explored in theories like cyclic cosmology. In this model, the universe undergoes endless cycles of expansion and contraction, with each cycle leaving imprints on the next. If true, dark flow could represent evidence of an earlier universe influencing our own. Such a scenario would radically alter our understanding of time, suggesting that the Big Bang was not the beginning of everything but merely the latest chapter in an eternal cosmic narrative. Adding complexity to the mystery is the role of anisotropies in the cosmic microwave background, CMB. The CMB is often described as the afterglow of the Big Bang, a faint radiation that pervades the universe and provides a snapshot of its conditions roughly 380,000 years after its birth. Anisotropies, small fluctuations in the CMB's temperature, reveal crucial details about the universe's composition and structure. However, they also raise questions about uniformity. If the universe began as a smooth, homogeneous entity, what caused these deviations? Could the forces behind dark flow have contributed to the formation of these irregularities, leaving their fingerprints on the earliest light we can observe? Theoretical models attempting to reconcile dark flow with the CMB data often involve non-standard cosmologies. For instance, some propose that the universe may be embedded in a larger, megaverse, where different regions have unique properties. These regions, separated by immense distances or hidden by the cosmic horizon, might interact through gravitational forces. If a neighboring region of the megaverse contains a massive structure, perhaps a colossal black hole or an ancient remnant of collapsed matter, it could exert a pull on galaxies within our universe, manifesting as dark flow. Others suggest that dark flow might be tied to quantum phenomena on a cosmic scale. The quantum nature of spacetime, though largely unobservable at human scales, may have played a significant role during the universe's infancy. Quantum fluctuations, magnified by cosmic inflation, could have created vast energy imbalances that persist today as large-scale anomalies. Could dark flow be the result of such a fluctuation, a scar left by the chaotic birth of spacetime itself? These hypotheses are not without their challenges. The idea of detecting influences from beyond the observable universe requires a paradigm shift in how we think about evidence and causality. Traditional scientific methods rely on observations and repeatable experiments, but studying phenomena like dark flow involves interpreting faint, indirect signals. This raises important philosophical questions. How do we define evidence when the subject of study lies beyond our observational reach? And how can we ensure the validity of conclusions drawn from such evidence? The controversy surrounding dark flow also highlights the limitations of current models. For instance, the standard lambda CDM model, lambda cold dark matter, successfully explains much of the universe's structure and evolution, from galaxy formation to the accelerating expansion driven by dark energy. Yet it struggles to account for anomalies like dark flow, suggesting that our understanding of the cosmos may be incomplete. Some physicists argue that resolving these anomalies might require revisiting foundational concepts, such as the nature of gravity or the role of higher-dimensional spaces. This brings us to the broader implications of dark flow for cosmic cartography, the science of mapping the universe. Modern technology has enabled us to create detailed maps of galaxies, dark matter distributions, and the CMB, offering an unprecedented view of the cosmos. However, these maps are inherently limited by the cosmic horizon. Dark flow challenges us to think beyond this boundary, to imagine what lies in the unobservable regions of space. Could we one day develop tools capable of seeing beyond the horizon, perhaps through advanced gravitational wave detectors or exotic particles that traverse dimensions? Efforts to understand dark flow also intersect with the search for dark matter and dark energy, the two dominant yet enigmatic components of the universe. While dark matter accounts for the gravitational forces that hold galaxies together, dark energy drives the universe's accelerating expansion. Both phenomena remain poorly understood, yet they could hold the key to solving the dark flow mystery. For instance, if dark matter exists in concentrated regions beyond the observable universe, it might exert a pull on visible matter, contributing to the large-scale motion we associate with dark flow. Similarly, the study of primordial black holes, hypothetical black holes formed in the early universe, has gained renewed interest. These objects, if they exist, could provide the mass required to influence galaxy clusters over vast distances. They might even serve as gateways to other regions of the universe, connecting disparate parts of spacetime through wormholes or other exotic phenomena. Could such black holes, hidden beyond our cosmic horizon, be the engines driving dark flow? The implications of dark flow extend far beyond astrophysics. They touch on questions about the nature of reality, the limits of human knowledge, and our place in the cosmos. If we accept that forces beyond the observable universe influence our own, it challenges the notion of a self-contained cosmos. It suggests that the universe is part of a larger, interconnected system, where boundaries are fluid and interactions transcend traditional definitions of space and time. As scientists continue to study dark flow, they are not just seeking answers to a specific question, they are exploring the edges of the knowable, pushing the boundaries of what it means to understand the universe. In doing so, they remind us of the beauty and wonder of science, the relentless pursuit of truth, no matter how distant or elusive it may seem. The mystery of dark flow urges us to confront the very architecture of the universe, asking us to reconsider whether we can ever fully grasp the forces at work beyond our observational limits. The idea of an unobservable realm pulling on visible matter introduces profound implications for science and philosophy alike. It suggests that what we see and measure is but a fraction of the universe's totality, leaving us to wonder what secrets lie beyond the cosmic horizon. One intriguing aspect of the dark flow phenomenon is how it may relate to the multiverse theory. If our universe is just one of many in a multiverse, then neighboring universes could exert gravitational influences on ours. These external forces might explain the peculiar directional movement of galaxy clusters. Imagine a scenario where another universe, possibly with its own unique laws of physics, exists just beyond our observational reach. Its immense mass or energy distribution could account for the pull causing dark flow. This would not only validate aspects of multiverse theory but also open the door to studying interactions between universes, an idea that seems straight out of science fiction yet finds increasing support in theoretical physics. Another line of inquiry involves cosmic inflation, the rapid expansion of the universe immediately after the Big Bang. Inflation theory posits that space itself stretched exponentially in a fraction of a second, smoothing out irregularities and creating the vast, largely homogeneous cosmos we see today. However, if inflation did not occur uniformly, it might have left behind imbalances in energy or mass distribution, leading to large-scale anomalies like dark flow. These remnants of inflationary processes could provide a direct link to the universe's earliest moments, offering clues about its origins and structure. This perspective is further complicated by the concept of brane cosmology, derived from string theory. In this model, our universe is envisioned as a three-dimensional brane, floating within a higher dimensional space. Other branes might exist in this hyperspace, and interactions between them could create observable effects in our universe. For instance, if a massive structure exists on a neighboring brane, its gravitational influence might extend across dimensions, tugging on galaxies in our brane and manifesting as dark flow. Such a scenario challenges traditional notions of gravity in space, suggesting that forces we perceive as local might have interdimensional origins. The observational evidence for dark flow primarily comes from studies of the kinematic Sunyaev-Zeldovich effect, which involves the interaction of cosmic microwave background (CMB) photons with hot gas and galaxy clusters. As photons pass through these clusters, they gain or lose energy depending on the cluster's motion relative to the observer. By analyzing these energy shifts, scientists can infer the velocity and direction of galaxy clusters. The persistent alignment of these motions toward a specific region of the sky is what defines dark flow. However, this evidence is not without its critics. Some scientists argue that the data might be skewed by observational biases or limitations in current methodologies. For instance, the large-scale structure of the universe, including superclusters and cosmic voids, could create localized gravitational effects that mimic dark flow. Others point out that the statistical significance of the phenomenon remains debated, with some studies suggesting that the observed motions could fall within the expected range of random fluctuations. Despite these challenges, the search for dark flow continues to inspire new technologies and observational strategies. Future missions, such as next-generation CMB observatories and deep space telescopes, aim to provide higher-resolution data that could confirm or refute the existence of dark flow. Additionally, advancements in gravitational wave astronomy may offer indirect ways to study the phenomenon. Gravitational waves, ripples in spacetime caused by massive cosmic events, could carry information about large-scale motions and interactions beyond the observable universe. If dark flow is confirmed, it would represent a paradigm shift in our understanding of the cosmos. It would force us to grapple with the idea that the universe is not an isolated entity but part of a larger, interconnected system. This realization would have profound implications for everything from cosmology to metaphysics, challenging us to rethink the nature of existence itself. Even if dark flow remains an unresolved anomaly, its study has already expanded the boundaries of scientific inquiry. It has pushed researchers to explore new theories, develop innovative tools, and confront fundamental questions about the universe's nature and origins. In this sense, the pursuit of dark flow embodies the essence of scientific exploration, the relentless quest to understand the unknown, driven by curiosity and the desire to uncover the truths that shape our reality. The mystery of dark flow also serves as a reminder of humanity's place in the cosmos. In the grand scheme of things, we are small, our lives fleeting compared to the vast, timeless expanse of the universe. Yet, despite our limitations, we have the unique ability to question, to seek, and to wonder. The study of dark flow is not just about solving a cosmic puzzle, it's about embracing the awe and wonder of existence, about daring to look beyond the familiar and venture into the unknown. As we continue to explore this enigmatic phenomenon, one thing becomes clear: the universe is far more complex, mysterious, and beautiful than we can ever fully comprehend. But perhaps it is this very incomprehensibility that makes it so compelling. Dark flow challenges us to imagine a universe without boundaries, to consider the possibility of forces and dimensions beyond our grasp, and to accept that some mysteries may remain forever unresolved. The implications of dark flow extend far beyond scientific curiosity. They strike at the heart of how we perceive the universe and our role within it. The observable universe, vast as it may seem, is only a fraction of the entirety of existence. Dark flow hints at the possibility that there are regions of the cosmos, or even realms beyond the cosmos, that we may never access or understand. This raises questions not only about the limits of human knowledge, but also about the nature of reality itself. If we consider the hypothesis that dark flow is caused by gravitational influences from massive structures outside the observable universe, we must then ask, what could these structures be? One possibility is that they are remnants of a pre-Big Bang universe. According to certain cosmological theories, our universe may be part of a cyclic process of birth, death, and rebirth. In this scenario, the structures pulling on our galaxy clusters might be relics of a previous universe, their gravitational imprint surviving the transition into our own. Another tantalizing idea is that these massive structures could be superclusters of matter from a parallel universe. In the framework of the multiverse theory, countless universes could exist simultaneously, each with its own physical laws and characteristics. If these universes are not entirely isolated but can interact through phenomena like gravity, it would provide a plausible explanation for dark flow. Such a discovery would fundamentally alter our understanding of the cosmos, suggesting that what we perceive as our universe is merely one bubble in an infinite cosmic foam. The possibility of parallel universes also raises philosophical and existential questions. If there are countless other universes, does that diminish the uniqueness of our own? Are there other versions of reality where life has evolved differently, or where the fundamental constants of nature are entirely alien to our comprehension? These questions, though speculative, are a natural extension of the dark flow mystery and the broader search for meaning in a universe that defies easy understanding. One particularly compelling avenue of investigation involves the study of the cosmic microwave background radiation, CMB. The CMB is a faint glow of radiation left over from the Big Bang, serving as a snapshot of the universe when it was just 380,000 years old. By analyzing subtle variations in the CMB, scientists have been able to map the large-scale structure of the universe and trace the movements of galaxy clusters. The peculiar motions associated with dark flow are seen as anomalies in this otherwise uniform radiation, pointing to forces at work beyond our observational limits. However, the CMB itself is not a perfect tool. Its signals are subject to interference from various sources, including our own galaxy, and interpreting its data requires complex models that are not immune to errors or assumptions. Despite these challenges, the CMB remains one of our best windows into the early universe and a crucial tool for investigating phenomena like dark flow. Advances in computational cosmology have also played a key role in studying dark flow. Using powerful supercomputers, scientists can simulate the behavior of the universe on both small and large scales, incorporating data from observations and theoretical physics. These simulations allow researchers to test different hypotheses about dark flow, exploring scenarios that might explain the phenomenon without requiring unobservable structures. For instance, some simulations suggest that dark flow could be a statistical fluke, a rare alignment of galaxy cluster motions that appears significant but is actually random. Yet, even if dark flow is eventually proven to be a statistical anomaly, Its study has already yielded valuable insights into the nature of the universe. It has forced scientists to refine their models of cosmic structure and dynamics, leading to a deeper understanding of phenomena like galaxy formation, gravitational interactions, and the distribution of dark matter. Dark matter itself is another factor that complicates the dark flow puzzle. This mysterious substance, which makes up about 27% of the universe's mass-energy content, does not emit or absorb light and can only be detected through its gravitational effects. If dark matter is unevenly distributed on cosmic scales, it could create localized gravitational forces that influence the motion of galaxy clusters. Understanding the role of dark matter in dark flow is therefore essential, but it requires unraveling one mystery to solve another, a daunting task that underscores the interconnectedness of cosmic phenomena. In addition to dark matter, dark energy, the mysterious force driving the accelerated expansion of the universe, might also play a role in dark flow. While dark energy is generally thought to act uniformly across space, creating a repulsive force that pushes galaxies apart, it is possible that variations in its distribution could influence the motion of galaxy clusters. This would add yet another layer of complexity to an already intricate puzzle, highlighting how little we truly know about the forces shaping the universe. The search for answers to dark flow is not limited to theoretical and observational cosmology. It also inspires collaborations between different fields of science, from particle physics to mathematics. For example, string theory, which attempts to reconcile quantum mechanics with general relativity, offers potential explanations for dark flow through its higher dimensional frameworks. These models suggest that what we perceive as the universe might be a three-dimensional brane embedded in a higher dimensional space. Interactions between branes could create gravitational effects that manifest as phenomena like dark flow. Despite the many theories and possibilities, one thing is clear: the study of dark flow pushes the boundaries of human understanding, forcing us to confront the limitations of our knowledge and the vastness of what remains unknown. It challenges us to think beyond the observable, to imagine a universe that is not confined by the limits of our perception or technology. This relentless pursuit of understanding is what defines the human spirit. We are creatures driven by curiosity, compelled to explore the unknown even when the answers seem out of reach. Dark flow, with all its mysteries and uncertainties, embodies this spirit. It reminds us that science is not just about finding answers but about asking questions that expand our horizons and deepen our appreciation for the universe's complexity and beauty. As we gaze into the depths of space, searching for the source of dark flow, we are not just looking outward, we are also looking inward, exploring the very essence of what it means to be human. The quest to understand this enigmatic phenomenon is a journey that transcends science, touching on philosophy, art, and the eternal human longing to know our place in the cosmos. This quest for understanding dark flow is, at its core, a testament to humanity's desire to push beyond boundaries. Every new discovery, whether it affirms or challenges existing theories, acts as a stepping stone in our larger journey to comprehend the cosmos. Dark flow, in particular, has ignited a global scientific dialogue, bringing together astronomers, physicists, cosmologists, and mathematicians in an unprecedented collaboration to uncover the truth behind this large-scale anomaly. One of the more provocative ideas surrounding dark flow is its potential to redefine the cosmological principle. This principle, a cornerstone of modern cosmology, asserts that the universe is homogeneous and isotropic on large scales. In simpler terms, this means the universe should look roughly the same no matter where you are or in which direction you look. Dark flow, however, seems to defy this principle. The coordinated movement of galaxy clusters toward a specific direction suggests a large-scale anisotropy, an unevenness that could challenge the foundations of our understanding of cosmic structure. If the cosmological principle were to be revised or overturned, the implications would ripple across multiple domains of science. Models of the universe's evolution, from the Big Bang to its current state, would need to be recalibrated. Theories about the distribution of matter and energy, the role of dark matter and dark energy, and even the ultimate fate of the universe might need to be revisited. Such a paradigm shift would not only reshape cosmology but also influence fields like particle physics and theoretical physics, where the nature of the universe plays a central role in defining research goals. In addition to theoretical ramifications, dark flow presents a profound observational challenge. The direction of this anomalous motion points toward a region of space beyond the observable universe, hidden by what scientists call the cosmic horizon. This horizon is the limit of what we can see, determined by the age of the universe and the speed of light. Anything beyond it is effectively invisible to us, as the light from those regions has not had enough time to reach Earth since the Big Bang. This limitation forces astronomers to rely on indirect evidence when studying dark flow. By analyzing the motions of galaxy clusters within the observable universe, scientists can infer the presence of forces acting beyond the cosmic horizon. This process requires extreme precision, as even small errors in data collection or interpretation could lead to misleading conclusions. Instruments like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have been instrumental in providing the high-resolution data needed for such analyses, but their findings remain subject to debate and scrutiny. Some researchers argue that the evidence for dark flow is not as robust as initially believed. They point to the possibility of statistical noise or observational biases that might mimic the effects of a large-scale flow. Others counter that the consistency of the observed motion across multiple galaxy clusters and different datasets strengthens the case for dark flow as a genuine phenomenon. This scientific back-and-forth highlights the importance of skepticism and rigorous testing in the pursuit of knowledge, ensuring that conclusions are based on the strongest possible evidence. The potential for new observational technologies to shed light on dark flow is an exciting prospect. Next-generation telescopes, like the James Webb Space Telescope and upcoming ground-based observatories, promise unprecedented clarity and sensitivity in observing distant galaxies. These instruments could provide additional data to refine our understanding of galaxy cluster motions, helping to either confirm or refute the existence of dark flow. Additionally, advances in gravitational wave detection might offer a complementary approach, allowing scientists to study the ripples in space-time caused by massive cosmic events and their potential connection to large-scale motions. The philosophical implications of dark flow are just as significant as the scientific ones. If this phenomenon is indeed caused by structures or forces beyond the observable universe, it raises profound questions about the nature of existence. What lies beyond the cosmic horizon? Is the universe infinite, or does it have a boundary? If there are regions of space we can never access or understand, how should that influence our conception of the universe and our place within it? Some thinkers have suggested that dark flow could be evidence of a higher dimensional reality. According to certain interpretations of string theory and related frameworks, the universe we experience might be a three-dimensional slice of a higher dimensional space. In this scenario, the structures causing dark flow could exist in these extra dimensions, exerting gravitational forces that bleed into our own three-dimensional universe. While speculative, this idea offers a tantalizing glimpse into a reality far more complex than what we currently perceive. Dark flow also intersects with the idea of cosmic inflation, the rapid expansion of the universe that occurred just fractions of a second after the Big Bang. Some models of inflation predict the existence of pocket universes, or bubble universes, that formed as different regions of space expanded at different rates. If these pocket universes exist, their gravitational effects could influence the motion of galaxy clusters in our own universe, potentially explaining dark flow. This connection between inflation and dark flow underscores how seemingly disparate aspects of cosmology can be deeply intertwined, each shedding light on the other. As researchers continue to grapple with dark flow, the phenomenon serves as a reminder of the vastness and mystery of the universe. It challenges us to think beyond the familiar and to consider possibilities that stretch the limits of our imagination. Whether dark flow is eventually explained through known physics, points to new discoveries, or remains an enduring enigma, it has already achieved something profound. It has expanded our sense of wonder and deepened our appreciation for the intricate, awe-inspiring nature of the cosmos. And so, as we look to the skies and ponder the forces shaping our universe, dark flow stands as both a mystery and a beacon. It calls us to continue exploring, questioning, and seeking answers, even in the face of uncertainty. For in that pursuit lies the true spirit of science, and the enduring legacy of humanity's quest to understand the cosmos. The pursuit of understanding dark flow represents more than just a quest for solving a scientific anomaly. It is a reflection of our unyielding curiosity about the universe. It invites us to challenge our assumptions and explore ideas that may fundamentally alter our perspective on reality. At its heart, this mystery exemplifies the delicate interplay between observation, theory, and the unknown. To fully appreciate the significance of dark flow, it is essential to delve deeper into the tools and methodologies that enable us to study such cosmic phenomena. The motion of galaxy clusters, critical to identifying the existence of dark flow, is typically measured using redshift and the cosmic microwave background radiation, CMB. Redshift occurs when light from a distant galaxy stretches as it travels across the expanding universe, shifting toward the red end of the spectrum. By studying the redshift of galaxies, astronomers can determine their velocity and direction of motion. The cosmic microwave background, meanwhile, serves as a snapshot of the universe approximately 380,000 years after the Big Bang. This faint afterglow of radiation provides a critical baseline for understanding large-scale motions in the cosmos. Scientists examine subtle temperature variations in the CMB to identify anomalies, like dark flow, that may point to external influences on galaxy clusters. Interestingly, the detection of dark flow required the development of highly sophisticated algorithms to isolate its signal from the noise in the data. The process involves combining observations from multiple instruments and analyzing them through advanced statistical methods. The result is a clearer picture of how galaxy clusters appear to be moving relative to the rest of the universe. However, this approach is not without controversy. Some skeptics argue that the observed motion could be a statistical artifact rather than evidence of an actual cosmic flow. Another intriguing aspect of dark flow is its potential connection to dark matter and dark energy, two of the most enigmatic components of the universe. Dark matter, which makes up about 27% of the universe's mass energy content, is thought to exert a gravitational influence on visible matter despite being invisible and undetectable through conventional means. Dark energy, on the other hand, is believed to drive the accelerated expansion of the universe and accounts for roughly 68% of its total energy density. Could dark flow be a result of interactions between galaxy clusters and concentrations of dark matter or dark energy beyond the observable universe? Some theories suggest that massive structures composed of dark matter might lie outside our cosmic horizon, creating gravitational effects strong enough to influence the motion of galaxy clusters within our visible universe. Similarly, variations in the distribution of dark energy could create anisotropies that contribute to the phenomenon of dark flow. While these ideas remain speculative, they highlight the intricate connections between different facets of cosmology. In the broader context, dark flow challenges us to consider the limitations of our observational tools and theoretical frameworks. The observable universe represents only a fraction of the total cosmos, an estimated 93 billion light-years in diameter. Beyond that lies the unobservable universe, a realm that may contain regions vastly different from what we know. It is in these uncharted territories that the cause of dark flow might reside, hidden from our current instruments, but not beyond the reach of human curiosity. The unobservable universe raises profound philosophical questions. If there are regions of space we can never see or interact with, can they truly be said to exist? How do we reconcile the notion of a finite observable universe with the possibility of an infinite cosmos? These questions go beyond the realm of science, touching on the nature of existence itself and humanity's place in the vast tapestry of reality. From a practical standpoint, the study of dark flow underscores the need for international collaboration and the pooling of resources to tackle complex scientific problems. Projects like the Planck mission, which provided crucial data on the cosmic microwave background, rely on teams of scientists, engineers, and policymakers from around the world. Similarly, future advancements in the study of dark flow will depend on the collective efforts of the global scientific community. The next generation of telescopes and observatories will play a pivotal role in this endeavor. Instruments like the Vera C. Rubin Observatory and the Square Kilometre Array are expected to provide unprecedented levels of detail in mapping the distribution of galaxies and their motions. These facilities will complement ongoing missions in space, such as the Euclid telescope, designed to study the dark universe. Together, they hold the promise of refining our understanding of large-scale cosmic phenomena, including dark flow. As we stand on the brink of these technological advancements, it is worth reflecting on how far we have come in our exploration of the universe. Just a century ago, the concept of galaxies beyond the Milky Way was still a matter of debate. Today, we routinely observe galaxies billions of light-years away and grapple with questions about the fundamental nature of reality. Dark flow, in this context, serves as a reminder of both our progress and the vast unknowns that still await us. Ultimately, the study of dark flow is not just about solving a specific mystery. It is about expanding the horizons of human knowledge. It is about embracing the challenges posed by the unknown and using them as opportunities for growth and discovery. Whether or not we ever fully understand dark flow, the pursuit itself is a testament to the resilience and ingenuity of the human spirit. The universe is vast, mysterious, and awe-inspiring. As we continue to probe its depths, dark flow stands as a symbol of our enduring quest to uncover the secrets of the cosmos. And in that quest, we find not only answers but also a deeper appreciation for the wonder and beauty of the universe we call home. The journey to uncover the mysteries of dark flow continues to demand extraordinary advancements in technology, collaboration, and theoretical exploration. As scientists refine their methods and develop new tools to explore the universe, they edge closer to unraveling the secrets of this large-scale anomaly. The stakes are high because dark flow could fundamentally reshape our understanding of physics, cosmology, and the very structure of the universe. One promising avenue of investigation lies in gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by massive cosmic events, such as the merging of black holes or neutron stars. The detection of these waves has already opened a new window into observing the universe. If dark flow originates from unseen massive structures beyond the observable universe, their gravitational effects might produce detectable perturbations in spacetime. Advanced gravitational wave detectors, like LIGO and Virgo, could provide indirect evidence of these hidden influences, offering a novel perspective on the phenomenon. Another critical tool in this quest is the study of cosmic voids, regions of space that contain far fewer galaxies than average. Cosmic voids are the opposite of galaxy clusters and provide an ideal environment for studying the large-scale motion of matter. By examining how galaxy clusters move relative to these voids, scientists can gain further insights into the forces driving dark flow. Future surveys of cosmic voids, combined with high-resolution simulations, could help clarify whether the anomaly is genuinely caused by external influences or if it is an artifact of current models. Theories involving multiverse scenarios also play a significant role in the discourse surrounding dark flow. One speculative idea suggests that our universe is part of a vast multiverse, a collection of many universes with varying physical laws and constants. If neighboring universes exist, their gravitational pull could potentially influence the motion of galaxy clusters within our own universe. This hypothesis is consistent with certain interpretations of string theory, which propose the existence of additional spatial dimensions and multiple universes as a natural outcome of the theory's framework. However, the multiverse hypothesis comes with its own set of challenges. Critics argue that it is inherently untestable because other universes, by definition, lie beyond our observable horizon. Without direct evidence, the multiverse remains a tantalizing but speculative idea. Nevertheless, indirect clues, such as the existence of dark flow, may provide a foothold for exploring this concept further. As the mystery of dark flow continues to evolve, it prompts broader questions about the nature of reality itself. For instance, what if the observable universe is just a localized bubble within a much larger cosmic structure? Could there be forces or entities in the unobservable universe exerting influence on us, much like unseen currents affect the surface of an ocean? These questions challenge us to think beyond conventional boundaries and consider possibilities that stretch the limits of human imagination. The philosophical implications of dark flow are equally profound. If we accept the idea that regions beyond the observable universe can exert a measurable influence on us, it forces us to confront the idea that our understanding of the cosmos is fundamentally incomplete. This realization is both humbling and exhilarating. It reminds us that science is a journey, not a destination, and that each discovery opens the door to new mysteries. From an educational perspective, the study of dark flow underscores the importance of cultivating curiosity and critical thinking. It encourages us to question assumptions, embrace uncertainty, and pursue knowledge for its own sake. The legacy of dark flow will not be measured solely by whether we solve the mystery, but by how it inspires future generations to explore the unknown. The public fascination with dark flow also highlights the role of science communication in bridging the gap between complex research and general understanding. Explaining phenomena like dark flow in accessible terms helps demystify science and fosters a sense of wonder about the universe. It also underscores the interconnectedness of humanity's quest for knowledge, showing that the pursuit of cosmic mysteries transcends. As we gaze into the vast expanse of space, it is clear that the universe holds countless secrets, yet to be uncovered. Dark flow is but one piece of a much larger puzzle, a puzzle that challenges us to think deeply, collaborate widely, and innovate boldly. With each passing year, our understanding of the cosmos grows, and with it, our ability to tackle questions that once seemed unanswerable. The search for the source of dark flow is a testament to the resilience and determination of the scientific community. It reminds us that even in the face of uncertainty, progress is possible through persistence, creativity, and collaboration. As we continue this journey, we do so with the knowledge that every question answered leads to new questions posed, a never-ending cycle of discovery that defines the human experience. In the grand scheme of things, dark flow is more than just a scientific anomaly. It is a symbol of the unknown, a beacon that guides us toward the uncharted territories of the universe. And in that sense, it is a reminder that the greatest mysteries often lie just beyond the horizon, waiting to be uncovered. The study of dark flow challenges us to stretch our minds to comprehend the enormity of the universe, as well as the forces that may lie beyond our ability to observe directly. Each discovery related to this cosmic anomaly forces us to revisit some of the most foundational concepts of cosmology, from the nature of gravity to the limitations of our observational tools. But what makes dark flow especially intriguing is how it serves as a focal point for so many intersecting disciplines, from theoretical physics to observational astronomy, from philosophy to advanced mathematics. One area of increasing interest is the role that quantum mechanics might play in explaining dark flow. Quantum mechanics, with its probabilistic and often counterintuitive nature, governs the smallest scales of reality, from particles to subatomic phenomena. While seemingly disconnected from the vast scales involved in galaxy cluster movements, some theories suggest a deep relationship between the quantum world and cosmic structures. Ideas like quantum entanglement and the holographic principle propose that large-scale phenomena could have roots in the quantum realm, creating an unexpected bridge between the microcosm and the macrocosm. In particular, the holographic principle proposes that the universe's information, the fundamental stuff that makes up reality, could be encoded on a two-dimensional surface, much like a hologram. If true, this would mean that the three-dimensional movements of galaxy clusters, including dark flow, might be manifestations of deeper, two-dimensional processes that lie beyond our observable universe. This principle, though still highly speculative, offers a tantalizing perspective on how unseen dimensions could influence our cosmos. Simultaneously, cosmologists are exploring the possibility that dark flow might be evidence for modified gravity theories. While Einstein's general relativity remains the cornerstone of modern physics, it is not without its challenges. Some alternative theories propose modifications to gravity at extremely large scales, which could explain anomalies like dark flow. For instance, theories such as modified Newtonian dynamics, and emergent gravity hypothesize changes to how gravity behaves when dealing with vast cosmic distances. If dark flow is driven by such a mechanism, it could signal a need to rethink the laws of physics that have guided our understanding for over a century. Moreover, dark flow has implications for the study of cosmic inflation, the rapid expansion of the universe immediately after the Big Bang. According to the inflationary model, the universe expanded exponentially in a fraction of a second, smoothing out irregularities and setting the stage for the large-scale structure we observe today. However, if dark flow represents an influence from beyond the observable universe, it could challenge or refine our understanding of how inflation occurred. It might suggest that the universe's initial conditions were more complex than previously thought, shaped by interactions with regions beyond our cosmic horizon. Such a paradigm shift would not only affect how we understand the early universe but also force us to reconsider the role of initial conditions in determining the large-scale structure of the cosmos. Are we merely a product of random chance, shaped by fluctuations in the early universe? Or is there a deeper, more deterministic process at work, influenced by factors we cannot yet observe? Dark flow, in its enigmatic persistence, keeps these questions alive. On a more practical level, dark flow continues to push the limits of technology and data analysis. Modern telescopes, such as the James Webb Space Telescope, have already begun providing unparalleled detail about the distant universe. As these instruments collect more data, scientists can refine their models and simulations, creating a clearer picture of how galaxy clusters behave over time. Computational power is also advancing rapidly, allowing researchers to run simulations of the universe at scales and resolutions that were unthinkable just a decade ago. These simulations help test various hypotheses about dark flow, ruling out some possibilities while reinforcing others. Despite all this progress, the scientific community remains divided over the ultimate nature of dark flow. Some researchers argue that it may not represent a genuine physical phenomenon but rather a misinterpretation of observational data. This skepticism underscores the importance of rigorous testing and peer review in the scientific process. However, even if dark flow were to be explained away as an artifact of measurement or analysis, the journey of exploring it would still have profound value. It would deepen our understanding of cosmic dynamics, inspire technological innovation, and fuel philosophical discussions about the nature of reality. At its core, the mystery of dark flow is a story about human curiosity and the unrelenting drive to make sense of the unknown. It reminds us that the universe is far larger, more complex, and more mysterious than we can currently comprehend. It also highlights the interconnectedness of scientific disciplines, showing how progress in one area, whether it's gravitational wave detection, quantum theory, or computational modeling, can shed light on seemingly unrelated phenomena. As we continue to explore the cosmos, we do so with the knowledge that each discovery brings us closer to answering some of the universe's most profound questions. Dark flow stands as a testament to the enduring allure of the unknown, a cosmic enigma that challenges us to look beyond the familiar and venture into uncharted territory. And yet, even as we uncover more about this mysterious phenomenon, we are reminded that the universe will always hold secrets just out of reach, enticing us to keep searching, questioning, and dreaming. Dark flow is not just an anomaly, it is a call to action, a reminder that the journey of discovery is as infinite as the cosmos itself. The pursuit of understanding dark flow has led to numerous breakthroughs in both theoretical and observational astrophysics. As our technology improves and new tools come into play, scientists are continuously refining their hypotheses and testing their limits. Dark flow has reignited interest in some of the most fundamental questions about our universe, and has expanded the scope of scientific exploration in directions we could never have imagined. One critical aspect of dark flow that continues to capture the imagination of scientists and the public alike is the possibility that it might represent evidence for something beyond the known universe. As we examine this phenomenon more closely, we find that dark flow could be suggesting that our universe, as we understand it, is not the only one. The implications of this are immense. If there are indeed other universes exerting influence on our own, it could change everything we know about the laws of physics, the fabric of space-time, and even the nature of existence itself. This idea aligns with the concepts proposed by cosmological models like the multiverse theory, which suggests that what we perceive as the universe might actually be just one of many bubbles in a much larger cosmic foam. These bubbles could have different physical constants, laws of physics, and even different histories. The motion of galaxy clusters toward an unknown point, if it is indeed driven by external influences, might indicate that we are feeling the effects of gravitational forces from these other universes, a profound insight that could potentially open the door to understanding much larger structures in the cosmos. However, the multiverse hypothesis is still a matter of much debate. While it provides an elegant framework for understanding unexplained cosmic phenomena like dark flow, it also raises questions that challenge the limits of scientific inquiry. Chief among these is the issue of testability. How can we test the existence of universes beyond our own if we cannot observe them directly? Some scientists argue that, because the multiverse lies beyond our observable universe, it may not be a concept that can ever be verified using empirical evidence. This makes the multiverse an intriguing but speculative concept, one that demands further exploration, even if it's unclear whether it can ever be fully validated. While theoretical frameworks like the multiverse offer interesting avenues for investigation, observational evidence remains the cornerstone of scientific progress. In the case of dark flow, the motion of galaxy clusters presents one of the few observational anomalies that have the potential to lead us to a deeper understanding of the universe. If these galaxy clusters are indeed moving in ways that cannot be explained by our current models, then we must take a closer look at the forces at play. This movement might be a clue, perhaps a cosmic fingerprint pointing to the influence of something far beyond what we can directly observe. As mentioned earlier, gravitational waves could provide an important link between dark flow and external forces. If there are unseen, massive objects beyond our observable horizon, their gravitational effects might be detectable through the subtle ripples they create in space-time. Detecting these waves could offer the first concrete evidence of forces acting on our universe from the outside. However, this endeavor presents significant challenges, as the precision required to detect such minute disturbances is extraordinarily high. Current gravitational wave detectors are already pushing the boundaries of what is possible, but much work remains to be done before we can definitively link gravitational waves to phenomena like dark flow. Another promising area of research involves large-scale cosmological simulations. These simulations help us model the universe's evolution over vast periods of time, using supercomputers to calculate the effects of gravitational forces, dark matter, dark energy, and other factors on the cosmic landscape. By simulating different scenarios, scientists can determine whether the observed motion of galaxy clusters can be explained by known forces or if they require the introduction of new, exotic influences. Some of the most sophisticated simulations being conducted today are specifically designed to explore phenomena like dark flow, with the hope that they will reveal new insights into the nature of the universe's large-scale structure. As our models become more advanced and our observational capabilities more refined, the question remains: what, exactly, is driving the motion of these galaxy clusters? Is it a fundamental flaw in our current models of gravity, or is it something entirely new, something that challenges everything we think we know about the universe? The quest to understand dark flow will likely continue for many years to come, and the answers may not be as clear-cut as we would hope. The complexity of the universe, and the forces that govern it, may be far beyond our current ability to fully comprehend. But that, in itself, is the beauty of scientific discovery. Every new question we answer leads to more questions, and with each step forward, we push the boundaries of human knowledge just a little bit further. As we approach the limits of our understanding, it is important to remember that the universe is not a static entity. It is constantly evolving, and as we peer deeper into its vastness, we are likely to encounter even more phenomena that defy explanation. Dark flow is one such phenomenon, but it is unlikely to be the last. Just as the discovery of gravitational waves opened up a new era in astrophysics, so too might the study of dark flow lead us to entirely new realms of understanding. For now, the mystery remains unsolved, but the pursuit of answers continues to drive forward some of the most exciting and groundbreaking research in modern science. Whether or not dark flow is ultimately explained by new physics or new theories, Its very existence serves as a testament to the boundless curiosity that defines the human spirit. It reminds us that there is always more to discover, more to learn, and more to understand about the cosmos we inhabit. The search for answers will continue, as will the wonder that dark flow inspires in those who look up at the stars and wonder, what else is out there? The mystery may not be solved today, tomorrow, or even in the next decade, but the journey toward discovery will continue, because the universe has more to teach us than we can ever imagine. As we continue to explore the implications of dark flow, it's essential to remember that this anomaly is more than just a curious cosmic phenomenon. It's a symbol of how much we still have to learn about the universe. The motion of galaxy clusters toward a point beyond the observable universe is not something we can easily fit into our current models, but that doesn't mean it's beyond understanding. It's a challenge to push the boundaries of knowledge, to dare to ask the big questions and seek the answers to them. One of the most intriguing aspects of dark flow is the potential it holds for advancing our understanding of cosmology, the study of the universe's origin, structure, and eventual fate. Cosmology has made tremendous progress over the last century. We've gone from thinking the universe was static and unchanging to recognizing that it is dynamic, expanding, and evolving. The discovery of dark flow could be yet another key to unlocking a deeper understanding of the large-scale forces shaping the cosmos. The observable universe is defined by the furthest distance that light has been able to travel since the Big Bang, and this creates a natural boundary to what we can see. We know that this boundary is not the edge of the universe, but simply the limit of what can be observed with our current technology. Beyond this observational horizon lies what scientists refer to as the unobservable universe, a region of space that is effectively invisible to us. The motion of galaxy clusters detected as dark flow is directed toward a location beyond this boundary, leading to the possibility that we might be seeing the influence of something beyond the known universe, an unseen force that stretches far beyond the limits of our instruments. There are several potential explanations for why galaxy clusters would exhibit this unusual motion. One possibility is that they are being pulled by a massive, unseen gravitational source. This would suggest that there is an enormous concentration of mass located far beyond the observable universe. This object or region could be influencing the motion of galaxies in a way that we have not yet fully understood. This dark matter could represent an entirely new class of astronomical objects, things that exist but that we cannot yet detect directly. If dark flow is indeed caused by the influence of objects beyond our universe, then this could represent the first observational evidence of regions of space that exist outside the observable universe. This would not only be a significant discovery but would also open up new frontiers in the study of theoretical physics, where the concept of multiple universes or dimensions is still debated. Some cosmologists have suggested that the universe we observe is just one bubble in a vast, multidimensional structure, and the unexplained motion of galaxy clusters could be the result of interactions with other bubbles. This is an idea rooted in string theory and multiverse models, but it remains controversial due to the lack of direct evidence. Dark flow could be the evidence that string theory and the multiverse hypothesis need to become more than just theoretical ideas. One thing that we can be certain of, however, is that the existence of dark flow challenges our current understanding of cosmological principles. Traditional models of gravity and dark matter can explain much of what we see in the universe, but dark flow presents a phenomenon that requires new ways of thinking. If the force driving this motion is not fully explained by existing models, it could indicate the need for a fundamental shift in the way we approach the study of the universe. The very concept of dark flow challenges the foundations of cosmological models. If we accept that there are forces acting upon galaxy clusters from outside our observable universe, then we may need to consider the existence of other dimensions, other universes, or other physical laws that we are not yet capable of understanding. This could radically alter our understanding of the cosmological constant, dark matter, and the shape of the universe itself. It is an exciting and perplexing puzzle that continues to captivate the minds of astrophysicists. There's another compelling reason why dark flow is such an exciting discovery. It reminds us how much we still don't know. As humans, we've made incredible strides in exploring the universe, from landing on the moon to mapping the cosmic microwave background. Yet, for all our advancements, we're still only scratching the surface of the mysteries that lie beyond. Dark flow is a reminder that there are still forces out there that we don't fully comprehend, and it beckons us to continue asking questions and challenging the limits of our understanding. Every new discovery opens up new pathways for exploration. When we first discovered dark matter, it was an anomaly that didn't fit into our understanding of gravity. Today, dark matter is one of the most active fields of research in physics, with scientists racing to uncover more about this mysterious substance that makes up a significant portion of the mass in the universe. The same could happen with dark flow. As more data is gathered, more sophisticated models are developed, and new technologies are created, we may begin to unravel the nature of the forces driving this anomaly. In the future, next-generation telescopes like the James Webb Space Telescope or the Square Kilometre Array might provide the key insights needed to explore dark flow further. These powerful instruments will allow scientists to peer deeper into the cosmos than ever before, potentially unlocking clues that could explain the motion of galaxy clusters and the forces at play. With improved observational capabilities, the universe may reveal secrets that were once thought to be beyond our reach. The discovery of dark flow also highlights the importance of collaboration in science. Astrophysics is a highly interdisciplinary field, and the study of dark flow requires input from many different areas of expertise, including gravitational physics, cosmology, and high-energy astrophysics. Researchers from around the world are working together to understand the data, test hypotheses, and refine our models. This collaborative approach is essential for tackling complex problems and moving closer to the truth. Dark flow is more than just a scientific mystery. It's a symbol of the human drive to explore, to understand, and to challenge the unknown. As we continue to push the boundaries of our knowledge, we are reminded that there is still so much to discover in the vast and enigmatic universe. Whether dark flow is eventually explained by a new physical theory, or whether it opens the door to entirely new realms of understanding, it will undoubtedly play a key role in the next chapter of our exploration of the cosmos. As we continue to look deeper into the universe, the motion of galaxy clusters toward an unknown point beyond the observable universe may prove to be one of the most significant discoveries in modern science. For now, the mystery remains, but the journey of discovery is far from over. As we continue to explore the enigma of dark flow, it's important to note how it could potentially reshape the future of cosmology and our understanding of the universe. Although much of the phenomenon still remains shrouded in mystery, one thing is for certain: dark flow is forcing us to rethink the way we look at the universe and our place in it. In science, one of the most thrilling moments comes when a theory is tested, and the results do not match our expectations. We see this with dark flow. It doesn't fit neatly into our standard models of the universe, and yet it exists in the data, challenging us to dig deeper and ask the hard questions. Could it be that dark flow is simply an anomaly, a result of some statistical fluke that hasn't yet been accounted for? Or could it point to something much more profound? If dark flow represents a real, large-scale cosmic force, it could fundamentally change how we think about the structure and origin of the universe. For one, it forces us to reconsider the uniformity of the cosmos. The prevailing view in modern cosmology, which is underpinned by the cosmological principle, holds that the universe is homogeneous and isotropic when viewed on a large enough scale. This principle has been instrumental in shaping our understanding of cosmic evolution, suggesting that the universe is largely uniform in its properties and structure. However, dark flow could challenge this view, suggesting that the universe is not as uniform as we once thought and that there may be large-scale, directional flows of matter and energy operating on scales much larger than our observable universe. What is especially puzzling about dark flow is its apparent connection to a region of space that we cannot see, beyond the observable universe. Our observations are limited to what we can detect with our instruments, and beyond the limits of what we can see, there's an enormous expanse that remains hidden from view. Dark flow suggests that there may be unseen forces, possibly from other regions of the universe, influencing the motion of galaxies in ways we don't fully understand. Could there be something massive, something extraordinarily dense, that lies just beyond the observable universe, affecting the motion of galaxies far away? Perhaps this region is too distant, too ancient, or simply too alien for us to perceive directly with current technology. This region could harbor phenomena that transcend our current theories of gravity, space, and time. The theoretical implications of dark flow extend far beyond cosmology. If we accept that galaxy clusters are moving toward an unseen point, it could also have a profound impact on our understanding of the fabric of the universe. It brings to the forefront the idea that there may be forces or laws at play that we have yet to uncover. While we rely heavily on the laws of physics that we understand, namely gravity and the expansion of the universe, dark flow seems to suggest that there may be unknown, larger-scale processes in motion. What if dark flow is related to something more fundamental than just gravity or matter? Some scientists speculate that it could be tied to high-energy physics or even quantum mechanics. In these realms, the behavior of space and time is still a mystery, and strange, unexpected phenomena can occur. The universe might be driven by forces or fields that we don't yet have the tools to measure directly. These fields could affect large-scale structures in the cosmos, such as galaxy clusters, in ways that we have never considered. This opens up the possibility that dark flow is a symptom of a deeper, more intricate web of interactions within the universe. The role of dark energy is another crucial piece of the puzzle. Dark energy is the name given to the mysterious force that is driving the accelerated expansion of the universe. Could there be a connection between dark energy and the strange motion of galaxy clusters? Some scientists have proposed that dark flow might be the result of interactions with a large-scale structure of dark energy that lies beyond the observable universe. This could help explain the apparent directional motion of galaxy clusters as they are drawn toward this unknown point. However, before we rush to conclusions, we must also recognize the possibility of observational bias. There is always the chance that we are misinterpreting the data. It's not uncommon in scientific discovery for phenomena to be perceived as anomalous at first, only for further research to show that they are explainable within the framework of known physics. The very nature of scientific progress often involves challenging what we think we know, only to refine our theories to accommodate new data. Therefore, while dark flow may indeed be a genuine mystery, it is also important to maintain a healthy skepticism and allow for the possibility that future observations could clarify or even disprove its existence. Even if dark flow does turn out to be a real phenomenon, explaining it may take years, or even decades, of further study. The data we have so far are based on observations of galaxy clusters moving in strange directions, but we need more detailed, precise measurements to confirm the existence of dark flow with greater certainty. The upcoming generation of telescopes and observatories, including the James Webb Space Telescope and the Square Kilometre Array, will be critical in providing more data. With more powerful instruments at our disposal, we may eventually be able to peer deeper into the universe, observe more galaxies, and track their movements with even greater accuracy. This could allow us to identify any hidden factors contributing to the motion of galaxy clusters and refine our theories accordingly. On a philosophical level, dark flow raises questions about the nature of knowledge itself. How much of the universe will we ever truly understand? We've made enormous strides, but each discovery seems to reveal even more questions than answers. Will the universe eventually reveal all of its secrets, or will we always be chasing after an unknowable mystery? The search for answers to dark flow may not just teach us about the cosmos, but about our own limitations as humans and our place in the vast expanse of space and time. Dark flow remains one of the most intriguing, perplexing, and exciting mysteries in modern astrophysics. The motion of galaxy clusters toward an unknown point beyond the observable universe challenges the very foundations of our cosmological models and calls into question the limits of our observational capabilities. Whether dark flow represents a new, unseen force at play in the universe, or whether it is the result of some unknown factor in our observations, it is clear that this phenomenon has the potential to reshape our understanding of the universe at the largest scales. As we continue to investigate this anomaly and gather more data, one thing is certain: dark flow will remain an enigma for years to come, pushing the boundaries of our knowledge and inspiring generations of scientists to look deeper into the unknown. As we continue to explore the implications of dark flow, it's crucial to address the larger context in which this phenomenon fits. Dark flow doesn't just represent a bizarre motion of distant galaxy clusters. It's a signal that there might be something fundamentally misunderstood about the universe itself. Understanding this anomaly could lead to a profound shift in how we approach cosmology, and even the laws that govern the universe at the most basic level. The concept of large-scale structures in the universe has been a key aspect of our cosmological models for decades. For a long time, we believed that the universe's large-scale structure was largely homogeneous and isotropic, meaning that it should look the same in every direction. However, dark flow challenges this assumption, suggesting that there might be hidden forces at play that disrupt this uniformity. Could it be that the universe, on the largest scales, is not as symmetric as we once thought? Could there be a pattern or force directing entire galaxy clusters toward a specific point in the distant cosmos, hidden beyond the reach of our current observations? This is where gravitational influences come into play. We have long known that gravity plays a dominant role in shaping the structure of the universe, influencing everything from the formation of stars and planets to the behavior of galaxies and galaxy clusters. However, the type of motion exhibited by these galaxy clusters is not easily explained by the gravitational forces we are familiar with. In the traditional model, gravity alone would not cause such a large-scale, coordinated movement. This suggests that there might be something even more powerful than gravity at work. Some scientists have proposed that this motion could be related to the cosmic microwave background (CMB), the afterglow of the Big Bang that permeates the entire universe. The CMB is a faint radiation that carries vital information about the early universe, and its study has been instrumental in shaping our current understanding of cosmology. If dark flow is somehow connected to the CMB, it could reveal a deeper connection between the earliest moments of the universe and the motions of galaxy clusters in the present day. This would not only change our understanding of the forces driving the expansion of the universe but could also offer a glimpse into the hidden, fundamental nature of reality itself. Dark matter is another aspect of this puzzle. For decades, we have known that a significant portion of the universe's mass is invisible to us. This mysterious substance, known as dark matter, interacts with ordinary matter through gravity but does not emit light or energy, making it extremely difficult to detect. Could dark matter play a role in dark flow? One hypothesis is that dark matter might be distributed in such a way that it influences the motion of galaxy clusters in a way we do not fully understand. While the connection between dark flow and dark matter remains speculative, the possibility is an exciting avenue for further research. Another intriguing possibility is that dark flow could be linked to other dimensions or even a parallel universe. While this may sound like science fiction, theories like string theory and multiverse hypotheses suggest that our universe could be just one of many, with dimensions beyond the familiar three that we experience. These higher dimensional spaces could potentially exert influence on the observable universe, explaining the strange, unexplained motion of galaxy clusters. If this theory proves true, it could mean that our understanding of space, time, and even the laws of physics would need to be radically revised. The notion of other universes or hidden dimensions existing alongside our own opens up a whole new realm of possibilities for scientific discovery. While observational bias remains a possibility, it is important to acknowledge the efforts that have been made to ensure the accuracy of dark flow's detection. The initial discovery of the anomaly came from data gathered by the Wilkinson Microwave Anisotropy Probe, WMAP, a spacecraft that was designed to study the CMB. Its observations showed an unexpected motion in the direction of a specific point in the sky, beyond the observable universe. This discovery was later corroborated by further studies using the Planck satellite and other advanced instruments. Despite this, the scientific community remains divided, with some skeptics arguing that the motion could be due to errors in the data or other unseen factors. The ongoing debate about the existence of dark flow highlights the scientific method at its best, the relentless pursuit of truth, even in the face of uncertainty. Researchers are continually refining their models and methods to better understand this phenomenon, and every new piece of data brings us closer to uncovering the nature of dark flow, or perhaps disproving it altogether. This process of skepticism, testing, and reevaluation is what drives scientific progress, and it is through this process that we are likely to unravel some of the most profound mysteries of the universe. As we look toward the future, the role of new technologies and improved observational tools cannot be overstated. The development of instruments such as the James Webb Space Telescope promises to offer deeper, more precise insights into the cosmos. Webb's ability to observe infrared wavelengths could provide a clearer picture of galaxy clusters at great distances, potentially shedding light on the mysterious motion that has puzzled scientists for years. The upcoming generation of radio telescopes, such as the Square Kilometre Array, will also play a pivotal role in mapping the large-scale structure of the universe with unprecedented accuracy. Moreover, the discovery of gravitational waves has opened up an entirely new field of observation, offering a new way to study the universe. While gravitational waves have not yet been directly linked to dark flow, their detection could provide valuable insights into the nature of the forces driving the motion of galaxy clusters. If gravitational waves are found to be related to dark flow, it could further support the idea that there are unseen, high-energy phenomena at play in the universe, forces that we have yet to fully comprehend. Beyond the scientific and technological advancements, dark flow also raises important philosophical questions. If the motion of galaxy clusters is indeed directed toward a specific point beyond the observable universe, what does this mean for our understanding of the universe's origin and purpose? For centuries, humanity has looked to the stars for answers to questions about our place in the cosmos. Dark flow may be a clue, an indication that there is much more to the universe than we currently know. The search for answers to this phenomenon is not just a quest for knowledge, it is a journey to understand the very nature of existence itself. Dark flow is not just an isolated anomaly, it is a gateway to new questions and deeper mysteries about the universe. Its discovery has forced us to reconsider our models of the cosmos, challenging long-held beliefs about the uniformity and structure of the universe. Whether it represents an unknown force, a flaw in our observations, or a clue to a deeper reality, dark flow offers an exciting opportunity for scientific discovery. As we continue to explore this phenomenon, we will undoubtedly uncover new insights into the nature of the universe, and perhaps even rewrite the laws that govern it. As we continue to contemplate the possibilities surrounding dark flow, it's important to address one of the most tantalizing aspects of the phenomenon: the idea that it could be linked to the structure of the universe itself. Our current models of cosmology, based on the Big Bang Theory and the observable universe, assume that the cosmos is relatively homogeneous and isotropic on large scales. This means that, statistically speaking, the universe should appear mostly the same in every direction, with the same physical laws and structures governing it. However, dark flow's implications challenge this assumption, suggesting that there might be larger forces, structures, or even patterns that we are not yet aware of. What if the universe is not as uniform as we once thought? What if there are hidden factors, perhaps originating from the very beginning of the cosmos, that influence the motion of galaxy clusters in ways we cannot yet fully grasp? Dark flow points us toward this possibility, hinting that the universe may have a far more complex structure than we currently understand. This opens up an entirely new area of exploration, where scientists could begin to investigate cosmological structures that extend far beyond the observable universe, potentially linked to pre-Big Bang events or even exotic, higher-dimensional phenomena that might govern the laws of physics in ways we are only beginning to explore. One particularly fascinating concept that has been proposed is that dark flow could be related to cosmological horizons, the boundaries beyond which we can no longer observe or measure due to the finite speed of light and the expanding universe. It is thought that the motion of distant galaxy clusters might be influenced by regions of spacetime beyond the limits of our observation. These regions could be gravitationally interacting with our observable universe in subtle ways, resulting in the directional motion we observe. If this is the case, then dark flow could offer a glimpse into parts of the universe that are effectively hidden from us, beyond our cosmic horizon. Furthermore, the role of dark energy, the mysterious force driving the accelerated expansion of the universe, could also be connected to dark flow. While dark energy is known to be a key factor in the large-scale dynamics of the cosmos, its exact nature remains one of the biggest mysteries in modern physics. Could dark flow be an indication that dark energy is not just accelerating the expansion of space, but also exerting a kind of directional influence on galaxy clusters? This idea remains speculative, but the connection between these two phenomena is intriguing and worthy of further investigation. If dark energy is indeed responsible for the motion of these galaxy clusters, it would not only reshape our understanding of the universe's expansion but also provide new insights into the fundamental forces that govern everything from subatomic particles to the largest cosmic structures. Another exciting avenue of research is the possibility that dark flow could offer evidence for interuniversal interaction. If there are indeed multiple universes, an idea that stems from theories like the multiverse or string theory, then it's possible that our universe could be interacting with others, even at the largest scales. These interactions could influence the motion of objects within our universe, including galaxy clusters. Imagine a scenario where a neighboring universe, with its own physical laws and properties, exerts a gravitational pull on our own universe, affecting the behavior of matter on a cosmic scale. While this remains speculative, the possibility that our universe could be influenced by forces outside of it challenges the very nature of existence itself, and invites a complete rethinking of the cosmos. Dark flow also invites us to revisit the concept of cosmological evolution. The universe has evolved over billions of years, and its large-scale structures have gradually formed through the interplay of gravity, dark matter, and the other forces that govern the cosmos. However, the discovery of dark flow suggests that this process of evolution might not be as simple or straightforward as we once believed. Could the universe be undergoing a new phase of evolution, driven by unknown forces or interactions? Could dark flow be a signal that we are on the brink of a major shift in our understanding of the cosmos? As scientists continue to study this phenomenon, it could lead to entirely new theories of cosmological evolution that expand our understanding of how the universe has come to be. In addition to these broader cosmological implications, the study of dark flow could also shed light on the very foundations of physics. The anomaly challenges some of our most fundamental assumptions about the universe, particularly those related to cosmic expansion, gravitational dynamics, and the uniformity of the universe. If dark flow is confirmed as a real phenomenon, it could signal that there are aspects of the laws of physics, whether related to gravity, dark matter, dark energy, or something else, that we have yet to fully understand. This could lead to major breakthroughs in theoretical physics, including the potential discovery of new physical principles or forces that have remained hidden for eons. At the same time, dark flow represents a unique opportunity to test our current models of cosmology and physics. If the anomaly is real and can be confirmed with more precise measurements, it could lead to the development of entirely new theories of cosmic structure and evolution. It might force us to re-examine our understanding of the Big Bang, the nature of space-time, and even the fundamental forces that govern the universe. For scientists and researchers, dark flow is both a puzzle to solve and a source of inspiration for new ideas and discoveries. In light of all these possibilities, it's clear that dark flow is much more than just a mysterious motion of distant galaxy clusters. It's a key that could unlock a whole new level of understanding about the universe. Whether it turns out to be the signature of hidden dimensions, the influence of dark matter or dark energy, or a signal of interaction with other universes, dark flow presents an exciting opportunity for cosmologists, physicists, and astronomers to probe the deepest mysteries of existence. Its study could change everything we thought we knew about the cosmos, from its origins to its future. As we stand on the precipice of this new frontier in cosmology, one thing is certain: the journey to understand dark flow will undoubtedly take us deeper into the heart of the universe than we've ever gone before. With each new observation, experiment, and hypothesis, we inch closer to uncovering the true nature of the forces at play on the largest scales. Dark flow might ultimately be one of the greatest mysteries of our time, a mystery that challenges the very limits of human knowledge and imagination. But even as we look to the future, we must remember that the search for answers is an ongoing process, one that will continue to evolve as we gain new tools, technologies, and insights. The universe is vast, and our understanding of it is still in its infancy. What we know now is only a small fraction of what is yet to be discovered. Dark flow is just the beginning, a stepping stone toward unraveling the greatest cosmic mysteries that lie ahead. Only time will tell what the future holds, but for now, the enigma of dark flow remains one of the most intriguing puzzles in the universe. As we continue to investigate the potential consequences of dark flow, it becomes increasingly clear that the phenomenon is much more than a passing curiosity. It could be a key to unlocking answers to some of the biggest questions in cosmology and physics. The more we learn, the more we realize that dark flow could fundamentally reshape our understanding of the universe and its underlying structure. But what makes this even more intriguing is the uncertainty that surrounds it. It is a reminder that even in an era of incredible technological progress and sophisticated observation, there is still much about the cosmos that remains beyond our comprehension. One of the core aspects that make dark flow so captivating is its potential connection to the limits of our observable universe. We live in a vast cosmos, and our view is limited by the speed of light and the ongoing expansion of space. But what if there is something beyond our current ability to observe? Something that lies beyond the very cosmic horizon, the boundary beyond which no information can reach us. Could dark flow be a subtle signal from this unreachable realm? It is an idea that forces us to reconsider the concept of the observable universe as we know it, pushing the boundaries of what is possible to detect and comprehend. It's important to recognize that our view of the universe is not static, it is constantly evolving. Our tools of observation and measurement are becoming more advanced, with each new generation of telescopes and space observatories offering deeper insights into the farthest reaches of space. As our technology improves, we may begin to uncover even more anomalies, stretching the limits of our understanding. Dark flow may be just one of many mysteries waiting to be discovered, and it could lead to the development of entirely new branches of science dedicated to exploring the unknown regions of the cosmos. There is also the possibility that dark flow could be related to the formation and behavior of supermassive black holes. Supermassive black holes are some of the most enigmatic objects in the universe, and they exist at the centers of nearly every large galaxy. They are incredibly powerful gravitational wells, capable of influencing the motion of entire galaxy clusters. Could the observed motion of these clusters be tied to the influence of supermassive black holes, either in our own galaxy or in a distant part of the universe? While this idea remains speculative, it is an area of research that could yield exciting results in the near future. In addition to its potential ties to black holes, dark flow may also be related to the large-scale structure of the universe. The cosmos is not evenly distributed. Matter is concentrated in vast galaxy clusters and superclusters, forming a kind of cosmic web. The motion of galaxy clusters observed in dark flow could be a sign that the universe is structured in ways we have yet to fully understand. It could indicate the presence of vast cosmic forces, structures, or even unknown entities that are influencing the universe's evolution on a grand scale. Another fascinating direction for future research lies in the potential connection between dark flow and quantum mechanics. As we delve deeper into the mysteries of the universe, it's becoming increasingly apparent that the realms of quantum physics and cosmology are far more interconnected than we initially thought. The strange and counterintuitive behaviors of particles at the quantum level could have implications for the large-scale motion of galaxies. Could dark flow be a manifestation of quantum effects playing out on cosmic scales? It's a possibility that invites further exploration, as quantum gravity, string theory, and other advanced theories could hold the key to unlocking the true nature of this phenomenon. If dark flow is indeed real and its effects are as profound as they seem, it will challenge many of our most deeply held assumptions about the laws of physics. The very idea that the universe might not be as uniform as we thought could have profound implications for everything from theories of gravity to our understanding of space-time itself. For centuries, scientists have relied on the assumption that the universe is relatively homogeneous on large scales. Dark flow casts doubt on this assumption, hinting that there might be larger forces, structures, or influences at play, ones that lie beyond our current understanding. In this context, dark flow could become a crucial puzzle piece in the search for a unified theory of everything, a grand theory that would combine all known forces of nature, gravity, electromagnetism, the strong force, and the weak force, into a single, cohesive framework. The mysterious motion of galaxy clusters may offer valuable insights into how these forces interact on cosmic scales, possibly leading to breakthroughs in our understanding of the fundamental nature of reality. As we continue to study dark flow and its implications, we must also consider the potential for interdisciplinary research to play a role in solving this cosmic puzzle. Theories and concepts from various branches of science, including astronomy, physics, cosmology, and even philosophy, could converge to provide a fuller understanding of what dark flow might be. For instance, the concept of a multiverse, suggesting that our universe is just one of many, could offer an intriguing framework for understanding the strange motion of galaxy clusters. If our universe is connected to others, this could explain the unaccounted-for forces acting upon it. The idea of multiple universes interacting with one another remains one of the most profound and mind-bending possibilities in modern physics. Dark flow could even inspire a shift in our thinking about the nature of time. Time, as we currently understand it, flows in one direction, from past to present to future. However, if dark flow is tied to cosmic structures or forces beyond our observable universe, it might suggest that time itself could be more flexible, or even multidimensional, than we currently comprehend. This could lead to a reevaluation of the laws governing causality, entropy, and the very fabric of space-time. As with many great scientific discoveries, the true impact of dark flow may only be understood with time. It is an idea that has sparked the imaginations of astronomers, physicists, and researchers alike, offering a tantalizing glimpse into the mysteries that lie beyond our comprehension. The implications of this phenomenon are vast and far-reaching, and its resolution could lead to some of the most significant breakthroughs in the history of science. Dark flow might not just be a puzzle waiting to be solved, it could be the key that unlocks the door to a deeper understanding of the universe itself. Whether it turns out to be a fundamental aspect of the cosmos or a temporary anomaly, dark flow is a reminder that the universe is full of surprises, and our quest for knowledge is far from over. As we continue to explore the potential implications of dark flow, it's crucial to emphasize just how much this mysterious phenomenon could alter our understanding of the universe. While we have made great strides in mapping the cosmos, discovering phenomena such as dark matter and dark energy, dark flow hints at an even deeper layer of reality that might defy everything we've learned so far. This suggests that our cosmic models are far from complete, and new discoveries could radically change our perception of the cosmos. One intriguing aspect of dark flow that has garnered attention is its connection, or lack thereof, to known cosmological phenomena. It stands apart from the effects we typically associate with cosmic expansion, which is the acceleration of space itself, moving galaxies away from one another. This expansion, driven by dark energy, follows a predictable pattern and is well documented. However, dark flow represents something different: galaxy clusters moving in a uniform direction, a phenomenon that isn't accounted for by our current understanding of cosmic expansion. It's as though something is pulling these clusters in a specific direction, possibly towards a region of the universe that lies beyond our observational reach. As we look deeper into the phenomenon, some questions emerge. What exactly is causing this mysterious flow? Could it be a gravitational anomaly from a distant region of space-time, or perhaps even an entirely new force that we haven't yet identified? The most exciting and unsettling possibility is that it's a signal from something that exists outside our observable universe. If this is the case, dark flow could be one of the first clues we've received from realms of existence beyond our ability to detect, forces or objects that have no place in our current understanding of physics. The notion of a force acting from beyond our visible universe brings to mind the idea of the multiverse. The multiverse theory suggests that our universe is not the only one that exists, but rather part of a vast collection of universes, each with its own laws of physics and perhaps even its own fundamental constants. If the motion of galaxy clusters is being influenced by something beyond our universe, it could be a signal of the interaction between our universe and another, perhaps a neighboring universe within a larger multiverse framework. This idea, while speculative, would suggest that the cosmos is far more interconnected than we currently imagine, and that forces beyond our immediate observation might have a profound impact on the behavior of galaxies on a cosmic scale. This brings us back to the problem of observable limits. The universe is finite, and the light from distant galaxies takes billions of years to reach us, which means that there are parts of the universe we will never be able to see, at least not with current technology. Yet, if dark flow is indeed a result of interaction with a region beyond our observable universe, it might represent a rare opportunity to glimpse something that exists far beyond our reach. It forces us to reconsider what it means to observe the universe, and whether there are regions of space that we cannot observe but that still exert a powerful influence on the observable cosmos. The implications of dark flow extend beyond just our understanding of space and time. They also call into question our understanding of cosmological physics. If this motion is real, it suggests that there might be large-scale cosmic forces at play that we have not yet accounted for. Could there be an entirely new form of gravitational interaction, or a previously unknown particle or field that is influencing the movement of these galaxy clusters? Could the cosmological constant, which represents the energy density of empty space, be influenced by unknown factors that cause this motion? While these questions are difficult to answer with certainty, they open up exciting avenues for further research into the fundamental forces that govern the universe. One area that could benefit from a deeper investigation is the large-scale structure of the universe. Our current understanding tells us that the universe is not a random scattering of galaxies and stars, but rather a highly structured cosmic web. This web is made up of clusters of galaxies, superclusters, and vast voids between them, creating a complex, interconnected network across the cosmos. The motion of these galaxy clusters, especially if dark flow is real, could provide us with valuable insights into the way these structures have formed and evolved over billions of years. Understanding how these large-scale structures interact, and whether they are being influenced by external factors, could be key to refining our models of the universe's formation and evolution. Moreover, as we delve into this phenomenon, we cannot ignore the possible role of dark matter and dark energy. These two invisible and mysterious components make up the vast majority of the universe's mass and energy, yet we still have only a limited understanding of their properties. Could dark flow be connected to the unknown distribution of dark matter? If dark matter is indeed the dominant form of mass in the universe, its gravitational influence could be responsible for the motion of galaxy clusters. Alternatively, could dark flow be a result of dark energy, the enigmatic force driving the accelerated expansion of the universe? These questions are far from being resolved, but they point to the need for more comprehensive research into the relationship between these cosmic phenomena. On a more speculative note, some researchers have even suggested that dark flow might be linked to extra-dimensional forces, potentially hinting at the existence of higher spatial dimensions. This idea emerges from theories like string theory and brane cosmology, which propose that our familiar three-dimensional universe is just a small part of a higher-dimensional space. If these theories are correct, it's possible that dark flow could be a manifestation of forces acting from these higher dimensions, influencing the movement of galaxies in ways that we cannot yet directly perceive. This would radically alter our understanding of the fundamental nature of space-time, suggesting that the universe is far more complex than we currently appreciate. Despite the many exciting possibilities, the reality of dark flow remains elusive. Its true cause, whether it's a gravitational anomaly, a sign of interuniversal interaction, or something else entirely, is still uncertain. This uncertainty only adds to the allure of the phenomenon. It is a puzzle waiting to be solved, one that could unlock new realms of scientific discovery and reshape the landscape of cosmology. At the heart of this mystery lies the profound truth that there is still so much we don't know about the universe. While we have made incredible strides in our understanding of space, time, and the forces that govern the cosmos, there are still deep questions that defy explanation. Dark flow is just one example of the many mysteries that remain unsolved, waiting for the next generation of astronomers, physicists, and cosmologists to unravel. It serves as a reminder that, no matter how much we learn, the universe is always full of surprises, and there are still countless mysteries waiting to be discovered. As scientists continue to observe and study the universe, we may one day find that dark flow is not just an anomaly, but a clue to something far more profound, a breakthrough that leads us to new realms of understanding, not just about the cosmos, but about the very nature of reality itself. Until then, dark flow remains a cosmic enigma, a puzzle that continues to intrigue and challenge us, urging us to reach farther and think deeper about the universe we call home. The mystery of dark flow is deeply entangled with the limitations of our current observational tools and the boundaries of human knowledge. As we explore further, we face a fundamental challenge. How do we study something that is not only beyond our reach but possibly beyond our understanding? This is the central problem with many of the most profound space mysteries. We know they exist, but comprehending their true nature requires advancements in both technology and theoretical physics. To truly unlock the secrets of dark flow, future space telescopes and other observation tools must be more sensitive and capable of detecting phenomena in ways that go beyond our current reach. Projects like the James Webb Space Telescope, JWST, which was designed to observe the universe in infrared wavelengths, are a step in this direction. However, the JWST and other space telescopes still operate within the observable universe, the portion of the universe that is accessible through the light and radiation that can travel to Earth. The limits of observation are not just a physical challenge, they're also deeply philosophical. Our understanding of the universe is limited by the fact that we cannot observe everything. There may be forces, objects, or phenomena acting on galaxy clusters that are simply too far away to see, but that still influence the way galaxies move. If dark flow is related to an influence beyond the observable universe, it would challenge the very idea of what we consider to be knowable. It may force us to redefine the boundaries of knowledge and cosmology, pushing the limits of science to explore realms that are currently unimaginable. In the quest to understand dark flow, it's also necessary to consider the role of mathematical models. Physicists and cosmologists rely heavily on mathematical equations and simulations to predict the behavior of galaxies, clusters, and other cosmic phenomena. However, the precise motion of galaxy clusters in the direction suggested by dark flow does not seem to fit neatly into any of these existing models. The lambda-CDM model, which is the current standard model of cosmology, relies heavily on assumptions about the distribution of dark matter, dark energy, and the expansion of space. Yet dark flow's presence seems to defy these assumptions, suggesting that something is missing in the way we understand large-scale cosmic dynamics. Some scientists have proposed that this anomaly could be the result of previously unaccounted for gravitational forces, potentially from unseen structures far beyond the edge of the observable universe. Others suggest that dark flow could be the signature of an ancient interaction with another universe, where the laws of physics may differ drastically from our own. Both theories are speculative, but they demonstrate the types of bold thinking that are required to tackle such an elusive phenomenon. If dark flow is indeed the result of some large-scale cosmic interaction, it could lead to an entirely new area of astrophysical research. Scientists would need to explore ideas like cosmic strings, multidimensional space, and extra-universal forces. These concepts, often found in theoretical physics, could help explain how an invisible force could cause massive cosmic objects to move in a particular direction, even from beyond the observable universe. But what if dark flow is not just a gravitational anomaly? What if it's a symptom of a much more profound problem in our understanding of space-time itself? The question that follows this line of thought is, could the fabric of space-time be far more complex than we think? Could there be deeper, hidden layers of reality where different physical laws apply, and where forces interact in ways we can't currently measure or understand? This idea, though speculative, suggests that the structure of the cosmos may be far more intricate than we currently grasp. Interestingly, the possibility of dark flow influencing the large-scale motion of galaxies leads to further questions about the future of our universe. If there are forces beyond the observable universe that can exert a pull on galaxies, might these forces have any impact on the fate of the universe itself? Could dark flow be a sign that the universe is not just expanding uniformly, but that there are forces pushing and pulling at the very fabric of cosmic existence, reshaping the way galaxies, clusters, and superclusters evolve? There are also more practical implications for the study of dark flow. It has already influenced the way astronomers think about the large-scale structure of the universe. Understanding the movement of galaxy clusters is crucial for constructing accurate models of cosmic evolution, and dark flow, with its unexpected motion, could help shape new approaches to modeling the universe's behavior. If future observations can provide more data on dark flow's trajectory and possible origin, they could lead to breakthroughs in cosmology that would alter our understanding of the universe in profound ways. Moreover, dark flow may offer a rare opportunity to test some of the most speculative and far-reaching ideas in modern physics. It could provide indirect evidence for theories like brane cosmology or higher-dimensional spaces, areas that have long remained speculative but are gaining traction in some circles. The very possibility that dark flow might be caused by interactions with other universes or dimensions opens up an entirely new field of research that could bridge the gap between classical physics and quantum mechanics. It challenges the boundaries between what we know and what we still have to discover. At the heart of the mystery is the fact that dark flow represents a cosmic phenomenon that cannot be easily explained by the current frameworks of cosmology. But this does not mean that it is beyond our understanding. The history of scientific discovery is full of examples where phenomena initially seemed incomprehensible or impossible, only to be explained later by new theories, models, or technologies. The key to unraveling dark flow lies in persistence, collaboration, and innovation. The scientific community will need to continue working together, refining theories, and developing the next generation of observational tools. One important aspect of this ongoing investigation is the collaboration between different fields of science. While cosmologists and astronomers are at the forefront of the search for answers, researchers in theoretical physics, mathematics, and even computer science will play crucial roles in solving the dark flow mystery. Understanding its origins and nature may require combining insights from diverse areas of research, just as breakthroughs in other areas of science often rely on cross-disciplinary collaboration. As we continue to probe the universe's darkest corners, we must also remember that the search for answers is not just about solving a puzzle, it's about understanding the fundamental nature of reality itself. Dark flow might hold the key to unlocking the deepest mysteries of the universe, and in doing so, it could force us to reimagine the very fabric of space and time. As we look toward the future, we may find that dark flow is just the tip of the iceberg, and that our search for the truth about the cosmos will lead us to even greater revelations about the nature of existence. Dark flow is far from being the only anomaly that has perplexed scientists in recent years. In fact, the study of large-scale cosmic phenomena has often revealed unexpected results that defy traditional understanding. Some of these anomalies, like dark flow, point to a fundamental gap in our models, while others may suggest that we are only scratching the surface of an even deeper mystery. The exploration of phenomena beyond the observable universe pushes us into uncharted territory, both conceptually and physically. We've come to understand that the observable universe is limited by the speed of light and the finite time since the Big Bang. This means that there are regions of space that are so far away that their light hasn't had enough time to reach us. These regions, known as the cosmological horizon, represent a fundamental boundary to our knowledge. But what happens beyond this boundary? What if there are phenomena lurking just out of sight that could influence the motion of galaxies, as suggested by dark flow? If dark flow is indeed related to some unseen structure beyond the observable universe, we would be forced to reconsider not only our understanding of cosmic dynamics but also our conception of the universe's structure itself. The question arises, is the observable universe truly all that exists? Or could the universe be far larger and more complex than we can currently comprehend? The idea that the universe may extend beyond what we can observe challenges everything we thought we knew about the limits of space and time. One potential theory that could help explain dark flow in this context is the idea of cosmic inflation. This is the theory that the universe underwent a rapid expansion in the moments immediately after the Big Bang. During this inflationary period, space itself expanded faster than the speed of light, creating regions of spacetime that are causally disconnected from one another. If dark flow is somehow linked to this early period of cosmic expansion, it could provide a clue about how the universe evolved from a singularity to the vast cosmos we observe today. However, the concept of cosmic inflation remains controversial, and many aspects of it are still being debated. If the universe expanded exponentially during inflation, it could imply that there are regions of space that have never interacted with the observable universe. This could explain why we observe galaxy clusters moving in a particular direction, because they may be influenced by gravitational forces from parts of the universe that are effectively invisible to us. In this way, dark flow could be a manifestation of forces that were set in motion during the earliest moments of the universe's history. Furthermore, the theory of inflation leads to another intriguing possibility: the existence of a multiverse. The idea of the multiverse suggests that our universe is just one of many universes, each with its own physical laws and constants. If dark flow is a result of interactions between our universe and others, it could be evidence of the existence of parallel or alternate universes. These other universes could be located in higher dimensions or even in separate bubbles within a larger cosmological framework. The multiverse theory, while speculative, is gaining traction among some theoretical physicists, and dark flow could provide indirect evidence for its existence. The idea that dark flow might be influenced by another universe also raises profound questions about the nature of reality itself. What does it mean for our understanding of the cosmos if the universe is not a singular, isolated entity but rather one part of a vast, interconnected network of universes? This notion would fundamentally alter the way we think about space, time, and the forces that govern the universe. It could imply that the cosmos is far more intricate and layered than we have ever imagined. Yet, the scientific community remains divided on whether dark flow can be explained by such bold theories. Some argue that the anomaly might simply be a statistical fluke, a temporary blip in the cosmic data that will eventually be explained by conventional means. Others believe that it represents a real and profound challenge to our current understanding of physics. Regardless of which camp you fall into, there's no denying that the mystery of dark flow has captured the imagination of scientists and space enthusiasts alike. It serves as a reminder that, despite our incredible advancements in space exploration, the universe still holds many secrets that remain just out of reach. In the coming years, astronomers will likely continue to study the motion of galaxy clusters with greater precision. New instruments and more detailed observations may provide us with the answers we seek, or they could lead us down even more bewildering paths. The discovery of dark flow has already sparked a new wave of research into large-scale cosmic phenomena, and it's likely that future studies will yield even more mysteries to unravel. One of the most exciting aspects of this investigation is the potential for collaboration between different areas of science. As astronomers, physicists, and mathematicians work together to decipher the nature of dark flow, they will inevitably draw on knowledge from fields as diverse as quantum mechanics, general relativity, and string theory. The answers to dark flow may not be found in a single discipline, but rather through the synthesis of ideas from across the scientific community. Moreover, advancements in technology will likely play a crucial role in uncovering the true nature of this cosmic anomaly. Instruments like the ATACM, a large millimeter/submillimeter array, ALMA, which allows astronomers to observe the universe in wavelengths beyond the visible spectrum, could provide valuable insights into the motion of distant galaxies. Similarly, future space telescopes, such as the Nancy Grace Roman Space Telescope or the Louvre mission, are expected to have enhanced capabilities for detecting faint cosmic signals, including those that might be related to dark flow. While these technological advancements will undoubtedly improve our observational capabilities, they also raise the question of whether there is a limit to how much we can learn. As we peer deeper into space, we may reach a point where our tools and models are no longer sufficient to explain what we see. This is the nature of science. The more we learn, the more we realize how much we still don't know. Dark flow represents one of the great frontiers of modern cosmology, a mystery that may ultimately reveal much more than we anticipate. It challenges our assumptions about the universe and forces us to rethink what we know about the cosmos. As this exploration continues, it is crucial to remember that the search for answers is not just about solving a particular puzzle, it's about expanding our understanding of the universe itself. The mystery of dark flow could ultimately lead to breakthroughs in cosmology, physics, and even philosophy. If we can understand the forces at play beyond the observable universe, it could change our entire worldview, reshaping how we think about the past, present, and future of the cosmos. The mystery of dark flow may be just one chapter in a much larger story, one that has yet to be written. Whether we uncover its secrets in the near future or continue to search for answers for decades to come, one thing is certain: the universe is far stranger and more mysterious than we can imagine. The journey to uncover the truth will not only deepen our understanding of the cosmos, but also bring us closer to the fundamental nature of reality itself. As we continue to investigate the phenomena that could be causing dark flow, we find ourselves delving deeper into the very nature of space-time itself. The very fabric of the universe, as described by theories like general relativity, might be fundamentally more complex than we ever imagined. Our understanding of the vast distances and gravitational forces that shape the cosmos has been refined over centuries, but the existence of dark flow suggests that there may be forces at play that we have yet to identify. One key area that researchers have explored is the cosmic microwave background (CMB) radiation. The CMB is the faint glow of radiation left over from the Big Bang, and it is often referred to as the afterglow of the universe's creation. By studying this ancient radiation, scientists can trace the large-scale structure of the universe and gain insights into its early stages. Some scientists have proposed that dark flow could be linked to anomalies in the CMB, which might indicate the presence of unseen forces beyond the observable universe. However, this connection remains speculative, and much more research is needed before any conclusions can be drawn. In addition to the CMB, astronomers have also turned to galaxy surveys to further investigate dark flow. These surveys gather data on the positions and movements of galaxies across vast regions of the universe, allowing scientists to map out the large-scale structure of the cosmos. By comparing the motions of galaxy clusters over time, researchers can look for patterns that might hint at the existence of dark flow or other unknown phenomena. The sheer scale of these surveys is staggering, with millions of galaxies being observed across billions of light-years of space. Despite the immense challenges involved in studying dark flow, the potential rewards of this research are immense. If we can solve the mystery of this cosmic anomaly, it could unlock new insights into the fundamental nature of the universe. We might uncover hidden aspects of space-time, or perhaps discover new forces or dimensions that are influencing the motion of galaxies. The implications of such a discovery could be far-reaching, not only advancing our understanding of cosmology, but also reshaping our ideas about the laws of physics themselves. At the same time, the mystery of dark flow serves as a humbling reminder of how little we truly know about the universe. For all our technological advancements, we are still only able to observe a fraction of the cosmos. The vast majority of the universe remains hidden from our view, and it is possible that dark flow is merely one small clue in a much larger puzzle. If there are forces or structures beyond the observable universe, we may need to rethink the very nature of the cosmos and our place within it. This uncertainty is not unique to dark flow. Throughout the history of science, there have been countless discoveries that have forced us to reconsider our understanding of the universe. From the heliocentric model of the solar system to the discovery of the expanding universe, each breakthrough has opened up new questions and challenges. Dark flow could be the next great puzzle that pushes our knowledge to new heights, but it could also be a reminder of the limits of our current understanding. As scientists continue to study this enigmatic phenomenon, it is clear that we are standing at the edge of a new frontier in cosmology. Whether or not dark flow is ultimately explained by known forces or something entirely new, it represents a challenge to our current models and a call to explore deeper into the mysteries of the universe. The study of this phenomenon will likely lead to new tools, new theories, and new perspectives on the cosmos that will shape the future of space exploration for generations to come. While many questions remain, one thing is certain: dark flow has captured the imagination of scientists and space enthusiasts alike. Its potential implications are profound, and the search for answers promises to push the boundaries of human knowledge. In the coming years, as technology continues to advance and our understanding of the universe deepens, we may find ourselves closer to unraveling the mysteries of dark flow. But even if we do uncover the truth, it is likely that many more mysteries will arise to take its place. The universe is an endlessly complex and dynamic system, and our journey to understand it is only just beginning. Dark flow may eventually be explained by a combination of known forces and new discoveries, or it may remain an enigma that challenges us for years to come. Either way, it serves as a reminder that the cosmos is vast, unpredictable, and full of wonders that we are only beginning to comprehend. The search for answers will continue, driven by the curiosity and determination that has always propelled humanity's quest for knowledge. As we explore the farthest reaches of space, we are not only uncovering the secrets of the universe but also learning more about the limits of our own understanding and the infinite possibilities that await us. The future of cosmology is bright, and the study of dark flow is sure to be a significant part of it. Whether this phenomenon turns out to be a natural consequence of known forces or a sign of something entirely new, it is a testament to the complexity and wonder of the universe we inhabit. As we venture further into the unknown, we can only imagine what other mysteries await, and how our understanding of the cosmos will continue to evolve in the years ahead. As we look forward to the future of cosmological research and the study of dark flow, there are several exciting developments on the horizon. One of the most important tools for this research is the next-generation telescopes and space observatories that are being developed and launched in the coming years. These instruments will provide us with a more detailed view of the universe, allowing scientists to observe distant galaxies, galaxy clusters, and cosmic phenomena with unprecedented clarity. The James Webb Space Telescope, JWST, which has already begun its mission, is expected to play a pivotal role in this research. Unlike its predecessors, such as the Hubble Space Telescope, the JWST is designed to observe the universe in the infrared spectrum. This capability allows it to peer deeper into space, detecting objects that are otherwise obscured by cosmic dust or the expansion of the universe. With its powerful infrared sensors, the JWST may provide new insights into the large-scale movements of galaxy clusters, including the elusive dark flow. In addition to the JWST, other planned space observatories like the Nancy Grace Roman Space Telescope and Euclid, part of the European Space Agency's Space Science Program, are designed to map the structure of the universe and improve our understanding of its expansion. These missions are expected to offer a wealth of data on the distribution of galaxies, clusters, and dark energy, all of which may provide important clues about dark flow. But the mystery of dark flow is not just a question of observational data. It's also a puzzle that challenges our fundamental theories of physics. The existence of dark flow forces us to consider whether there are forces or mechanisms that lie beyond our current models of space and time. While the standard model of cosmology, which includes the lambda-CDM model, explains many observed phenomena, dark flow may indicate the presence of unknown variables or forces. Some scientists have suggested that dark flow could be a result of interactions between our universe and others in a multiverse scenario. According to multiverse theories, our universe is just one of many that coexist in a larger, higher-dimensional space. If this theory holds any truth, the motion of galaxy clusters could be the result of gravitational influences from a neighboring universe, pulling on our cosmos from the outside. This possibility has sparked intense debates within the scientific community, as it would require a radical revision of the laws of physics as we know them. Another possibility that has been proposed is that dark flow is related to dark energy, the mysterious force that is believed to be responsible for the accelerated expansion of the universe. Dark energy is thought to make up about 68% of the total energy content of the universe, yet its true nature remains one of the biggest unsolved questions in cosmology. If dark flow is connected to dark energy, it could represent a manifestation of this force on a large scale, affecting the motion of galaxy clusters in ways that we are only beginning to understand. Another area of speculation is that dark flow could be related to the topological structure of the universe. In mathematical terms, space-time could have certain properties or configurations that influence the motion of matter in unexpected ways. This could include phenomena such as gravitational anomalies or hidden dimensions that alter the way galaxies interact with each other on the grand scale. If this is the case, solving the mystery of dark flow may require us to develop new mathematical models that extend beyond the familiar laws of physics. As the quest to understand dark flow progresses, it's important to acknowledge the role that collaborative international efforts will play in this endeavor. The study of cosmic phenomena like dark flow requires the pooling of resources, data, and expertise from scientists all over the world. Large-scale projects like the International Space Station, ISS, which brings together scientists from different countries to conduct research, and international collaborations like the Event Horizon Telescope, EHT, which captured the first-ever image of a black hole, demonstrate the power of global cooperation in advancing our understanding of the universe. Moreover, private sector involvement in space exploration has been growing rapidly in recent years, and companies like SpaceX, Blue Origin, and others are working to develop new spacecraft and technologies that could further enhance our ability to study the cosmos. The increased investment in space exploration by both governmental and private entities means that the tools available for observing dark flow and other cosmic anomalies will only continue to improve, bringing us closer to unlocking the secrets of the universe. While the concept of dark flow is still shrouded in mystery, it has undoubtedly sparked a new wave of interest in the study of large-scale cosmic motion and the fundamental forces that govern the universe. As astronomers and physicists continue to investigate this phenomenon, they will undoubtedly uncover new insights that will challenge our current understanding of space-time and our place in the cosmos. Even if dark flow eventually turns out to be something entirely different from what we currently suspect, the journey of exploration and discovery will continue to push the boundaries of human knowledge. Each new mystery we encounter opens up new avenues of inquiry and innovation, and the study of dark flow is no exception. It represents the frontier of modern cosmology, and its resolution may unlock new aspects of the universe that we can scarcely imagine. The mystery of dark flow also serves as a reminder of the awe-inspiring scale of the universe. Even in the most technologically advanced age of space exploration, we are still only beginning to comprehend the vastness of the cosmos and the forces that shape it. Whether dark flow is the result of a new force, an unknown dimension, or a fundamental flaw in our current theories, it underscores the complexity and wonder of the universe. Our search for answers may be a long and difficult one, but it is a journey worth undertaking. The pursuit of knowledge about dark flow is not just about understanding one specific anomaly. It's about expanding the horizons of human knowledge and exploring the deepest questions of existence itself. As we continue to peer deeper into the cosmos, we may uncover not only the secrets of dark flow but also new mysteries that will shape our understanding of the universe for centuries to come. The universe is vast, mysterious, and full of surprises, and our quest to unlock its secrets is just beginning. The search for dark flow is not merely an academic pursuit. It is a quest that could fundamentally alter our understanding of the universe and our place within it. As we strive to uncover the true nature of this cosmic anomaly, we also embark on a journey that may lead to even greater revelations. What we discover about dark flow could unlock new dimensions of knowledge, expanding the horizons of science far beyond our current limits. One area where the discovery of dark flow might have profound implications is in our understanding of cosmic evolution. The motion of galaxy clusters towards an unknown point could provide us with a unique glimpse into the forces that have shaped the universe since its birth. Current models of cosmic evolution suggest that the universe has expanded from an extremely hot, dense state following the Big Bang, and has continued to stretch ever outward. Dark flow, however, suggests that this expansion may not be as simple as we have assumed. If there are large-scale forces pulling galaxy clusters in a specific direction, it could mean that there are dynamics at play that we have yet to fully comprehend. This could lead to a reevaluation of the Big Bang theory, the cornerstone of modern cosmology. While the Big Bang model explains many of the phenomena we observe in the universe, such as the cosmic microwave background radiation and the redshift of distant galaxies, it assumes that the universe is expanding uniformly in all directions. dark flow challenges this assumption, and its discovery could prompt scientists to reconsider our understanding of the early universe. Perhaps there were conditions at the beginning of the universe that we are still not able to observe or measure. Another possibility is that dark flow might reveal hidden aspects of the large-scale structure of the universe. The universe is not a uniform expanse, but rather is made up of galaxies and galaxy clusters that are interconnected by vast cosmic webs. These webs are the result of gravitational forces that pull matter together over time. However, the distribution of these galaxies and clusters is not entirely random. There are voids, filaments, and superclusters, all of which are arranged in patterns that we are still trying to fully understand. Dark flow could provide a new perspective on these large-scale structures, perhaps shedding light on how galaxies and clusters are influenced by forces that we are unable to detect with current technology. If the motion of these galaxy clusters is directed towards an unseen point, it could indicate the presence of a structure, perhaps an enormous gravitational anomaly, at the edges of our observable universe. This would mean that the large-scale structure of the universe is far more complex than we currently realize, with unseen forces playing a major role in its organization. Moreover, dark flow could have profound implications for our understanding of dark matter and dark energy. These two mysterious components of the universe make up about 95% of its total energy content, yet we know very little about them. Dark matter, which is thought to account for the gravitational effects that we observe in galaxies and galaxy clusters, has not been directly detected, but its existence is inferred from its gravitational influence on visible matter. Dark energy, on the other hand, is responsible for the accelerated expansion of the universe. Together, these two unseen forces are some of the most intriguing mysteries in modern physics. If dark flow is related to either dark matter or dark energy, it could provide us with a new avenue of research into these enigmatic forces. Scientists are constantly searching for ways to detect dark matter and understand the nature of dark energy, but both remain elusive. Dark flow may be a clue that leads us to a deeper understanding of these phenomena, revealing their true nature and helping us to integrate them into our models of the universe. One of the more exciting possibilities is that the motion of galaxy clusters due to dark flow could be related to quantum effects that we have yet to observe on a large scale. Quantum mechanics governs the behavior of particles on the smallest scales, but its influence is not well understood at macroscopic levels. Some scientists have speculated that there may be quantum phenomena that extend across vast distances, affecting the motion of galaxies and clusters in ways that we do not yet understand. If dark flow is a manifestation of these quantum effects, it could open up entirely new fields of research that merge the worlds of quantum mechanics and cosmology. As research into dark flow continues, it will also drive the development of new theoretical models. The mystery of dark flow challenges our current understanding of the laws of physics, and as such, it is likely to inspire a new generation of theories that seek to explain this phenomenon. These theories could push the boundaries of physics, perhaps even leading to a more unified theory that ties together general relativity, quantum mechanics, and other fundamental forces in a way that we have not yet achieved. The study of dark flow will also contribute to the ongoing debates about the nature of the cosmic horizon. The cosmic horizon is the limit of what we can observe in the universe, defined by the speed of light and the expansion of space. The farther away something is, the longer it takes for its light to reach us. However, the universe is expanding, and in some cases, distant objects are moving away from us faster than the speed of light. This means that there are regions of the universe that are beyond our observational reach, and as a result, we cannot see them. Dark flow raises the question of whether there might be forces, structures, or even entire regions of the universe beyond the cosmic horizon that influence the observable universe in ways we cannot yet detect. If dark flow is a result of interactions from beyond the observable universe, it could suggest that the limits of what we can observe are not as definitive as we once thought. There may be cosmic forces that extend far beyond the regions we can currently measure, and this could lead to a dramatic shift in how we think about the universe and its structure. As we continue to explore the mysteries of dark flow, we must remember that scientific discovery is often a process of trial and error, with many questions leading to more questions. Dark flow may not have a simple explanation, but that is what makes it so fascinating. The pursuit of knowledge about this cosmic anomaly is not just about finding an answer, but about expanding our understanding of the universe and pushing the boundaries of human knowledge. The study of dark flow serves as a reminder that we are still in the early stages of exploring the universe. Despite all the progress we have made, there is so much more to discover. The vastness of the cosmos and the mysteries it holds are far greater than we can imagine, and each new revelation opens up new possibilities for exploration. Dark flow is just one piece of the puzzle, and as we continue to investigate it, we may uncover even greater mysteries that will shape our understanding of the universe for years to come. The quest to understand dark flow is not just a scientific challenge, it is a reflection of our innate desire to understand the universe and our place within it. As we look to the future of space exploration and research, it is clear that the mystery of dark flow will continue to captivate the imagination of scientists and enthusiasts alike. Whether it is the result of a cosmic force, a hidden dimension, or something entirely unexpected, dark flow is a phenomenon that demands our attention. And as we continue to unravel its secrets, we may find ourselves closer to understanding the deepest truths of the cosmos. The idea that something as vast and unseen as dark flow might be influencing the motion of entire galaxy clusters toward an unknown point beyond the observable universe is nothing short of extraordinary. The implications of such a discovery extend far beyond our current understanding of astrophysics, and challenge some of the most fundamental concepts in cosmology. As we explore this anomaly further, we must also recognize the broader significance it has in reshaping our views about the universe and our ability to comprehend the cosmos on an ever-expanding scale. To understand the potential impact of dark flow, we must first consider the methods by which scientists have been able to identify its existence. The phenomenon of dark flow was first observed in 2008 by a team of astronomers led by Alexander Kashlinsky of NASA's Goddard Space Flight Center. Using data from the Wilkinson Microwave Anisotropy Probe, WMAP, the team noticed an unexpected motion of galaxy clusters. These clusters appeared to be moving at higher velocities than expected, as though they were being drawn toward a specific point in the sky. This discovery was not made overnight. For years, scientists have observed peculiar motions in galaxies and clusters, but it wasn't until the WMAP data became available that a clear pattern emerged. The galaxies, which are supposed to be evenly distributed in all directions due to the expanding universe, seem to be showing a collective drift in a particular direction. This observation suggested the presence of an unknown force, one that is acting on a large scale and could be fundamentally altering the course of cosmic expansion. However, it's important to note that the concept of dark flow doesn't come with a neatly packaged explanation. It is one of those rare phenomena in science that both excites and baffles. While the team of astronomers could confirm the existence of the flow, they were unable to explain what exactly was causing it. The unknown point toward which these galaxy clusters are moving remains elusive. There is no obvious source of attraction, no large gravitational mass, or visible structure to account for the motion. In fact, this is one of the most perplexing aspects of dark flow, the absence of a visible object or force that could be pulling these galaxy clusters in a specific direction. Theories abound, ranging from the suggestion that this motion might be the result of gravitational forces exerted by an enormous, unseen object far beyond the observable universe, to the possibility that dark flow is related to phenomena we have yet to discover, such as dark matter, dark energy, or even the existence of other dimensions. It is also worth noting that the movement of galaxy clusters is not a new concept in itself. Scientists have long known that gravity causes galaxies and galaxy clusters to move towards each other. The force of gravity between galaxies leads to the formation of large cosmic structures, such as superclusters and filaments. These movements, however, occur on much smaller scales and are generally understood within the framework of conventional physics. What makes dark flow different is the sheer scale of its impact. The motion of these galaxy clusters appears to be occurring at a level of cosmic order and magnitude that defies current models of the universe's expansion. In addition to the theories about large, unseen objects exerting gravitational pull, There are also hypotheses involving the cosmic microwave background radiation, CMB. The CMB is the afterglow of the Big Bang, and it provides a snapshot of the universe at a very early stage. By studying the CMB, scientists can glean information about the universe's expansion and large-scale structure. Some researchers believe that dark flow could be related to an interaction between the observable universe and regions beyond our cosmic horizon, where the CMB's patterns are influenced by forces that we currently cannot detect. Such theories point to the possibility that the universe is not as isolated as we once thought. Could it be that the universe is part of a much larger cosmic system, one that operates on scales and in ways that we cannot yet comprehend? If dark flow is an effect caused by interactions with parts of the universe beyond the cosmic horizon, it would have profound implications for our understanding of the universe's boundaries and its structure. One particularly provocative theory suggests that dark flow might be related to a phenomenon known as the multiverse. The idea that our universe is just one of many universes that exist within a larger multiversal framework. In this context, dark flow could be the result of gravitational interactions between our universe and another, and the mysterious motion of galaxy clusters could be the physical manifestation of this interaction. If such a multiversal connection exists, it would imply that the universe we observe is not an isolated system, but rather part of a vast, interconnected cosmos with other universes possibly influencing ours in ways we can't yet detect. However, there is another, more tantalizing possibility that suggests dark flow might have something to do with the very fabric of spacetime itself. Theoretical physicists have long been interested in the nature of spacetime and its relationship to gravity, particularly when it comes to large-scale structures. Some speculate that quantum fluctuations in the fabric of spacetime could give rise to unexpected effects on the motion of galaxies. These fluctuations might occur on scales so large that they could influence the motion of galaxy clusters, pulling them in a particular direction, and leaving behind a kind of dark trace that we can observe but cannot fully explain. If dark flow is indeed a manifestation of unknown forces within the quantum nature of spacetime, it could mark the dawn of a new era in our understanding of the universe. Rather than simply operating within the known laws of physics, dark flow could represent an entirely new aspect of reality, one that lies just beyond our perception, waiting to be uncovered. Moreover, the mystery of dark flow touches on our deepest philosophical questions about the nature of the universe itself. For centuries, humanity has been grappling with the concept of a universe that is both vast and incomprehensible. We have built models and theories to describe how the universe works, but each new discovery, from the discovery of dark matter to the realization that the universe is expanding, forces us to rethink our assumptions. Dark flow challenges us to confront the limitations of our knowledge and accept that there is much about the universe that remains beyond our current understanding. It serves as a reminder that, despite our best efforts to understand the cosmos, the universe is full of mysteries that may never be fully explained. In this sense, dark flow is not just a scientific puzzle. It is a philosophical and existential challenge, forcing us to confront the fundamental questions about reality, existence, and the boundaries of human knowledge. If dark flow does, in fact, prove to be a significant discovery, one that leads to new insights into the nature of the universe, it will change the course of science as we know it. It will prompt a reevaluation of the theories we rely on to describe the cosmos and inspire new ways of thinking about space, time, and the very fabric of reality. The continuing study of dark flow will no doubt lead to more discoveries and theories, some of which may challenge our most basic assumptions. As researchers work tirelessly to decode this cosmic enigma, the world will be watching, waiting for the moment when we finally understand what is pulling these distant galaxy clusters toward the unknown. Perhaps one day, we will discover that dark flow is merely one part of a much larger cosmic puzzle, one that stretches far beyond the limits of our current imagination. Whether or not we ever fully understand it, the pursuit of knowledge about dark flow will remain one of the most exciting and important quests in the history of science. The mystery of dark flow reminds us that the universe is full of surprises, and that no matter how much we learn, there is always more to discover. And in that discovery lies the potential for an even greater understanding of our place in the vast, unfolding cosmos. The pursuit to understand dark flow isn't just about understanding a singular anomaly. It also represents an overarching journey into the unknown reaches of the universe. As with many groundbreaking scientific discoveries, the ramifications of finding a definitive answer to dark flow extend beyond astrophysics. This mystery calls into question fundamental principles of cosmology and physics itself. If the motion of galaxy clusters can indeed be attributed to forces acting from beyond our observable universe, we may need to consider new physical paradigms, possibly even new laws of physics. Before diving further into these possibilities, let's pause to appreciate the extraordinary challenges that astronomers and physicists face when trying to study such an elusive phenomenon. One of the primary reasons dark flow is so perplexing is because it is observed through indirect methods. Unlike the motion of individual stars or galaxies, which can be traced using telescopes and other instruments, dark flow's effects are seen only in the movement of massive galaxy clusters. These clusters, which are themselves made up of countless galaxies bound together by gravity, are vast and distant, meaning that the signals we receive are weak and often difficult to interpret. Researchers rely on cosmic microwave background (CMB) measurements to study the distribution and motion of galaxy clusters. The CMB is essentially the faint afterglow of the Big Bang, radiation that permeates the entire universe and provides a snapshot of its early stages. However, studying the CMB to detect anomalies like dark flow requires extreme precision and careful interpretation. Tiny fluctuations in the CMB can provide critical data on the motion of galaxies and galaxy clusters, revealing patterns that might otherwise be hidden from view. Yet, the challenges don't stop at the tools and data. There is the issue of uncertainty. When it comes to interpreting the results of dark flow, many scientists remain cautious. While there is consensus that galaxy clusters are moving in an unusual way, the explanation remains unclear. The most significant obstacle is that this motion does not neatly fit into the current understanding of cosmic expansion. The universe's expansion, which was first discovered in the 20th century, is thought to be driven by the energy of dark energy. This force causes galaxies to move away from each other, suggesting that, over time, the universe itself is expanding at an accelerating rate. Yet dark flow appears to be in direct contradiction to this expansion. Rather than galaxies moving apart, entire clusters are moving in a specific direction, toward an unseen source. If dark flow turns out to be a genuine phenomenon, it may require a major overhaul of our understanding of cosmic expansion. For decades, cosmologists have accepted that the universe is expanding uniformly in all directions. If this new anomaly is real, then we would need to rethink the entire concept of universal expansion. Could it be that the universe is expanding unevenly, or is there an external force or influence at play that we've not yet accounted for? One of the most intriguing possibilities is the potential connection between dark flow and the large-scale structure of the universe. The universe is not evenly distributed with galaxies scattered randomly across space. Instead, galaxies and galaxy clusters form large structures such as filaments and voids that span vast distances. These structures are thought to be shaped by the pull of gravity, which can cause the galaxies within them to move in predictable ways. However, dark flow appears to defy this pattern. Instead of galaxies and galaxy clusters moving in accordance with the larger structures, it seems that they are moving in a specific direction, toward an unknown point in the cosmos. Could dark flow be related to a cosmic structure that we have not yet discovered? The idea of unseen, large-scale structures lurking beyond the observable universe is a tantalizing one. In fact, some theorists speculate that the movement of galaxy clusters could be the result of gravitational influences from objects or structures located beyond the cosmic horizon, the point beyond which light has not had enough time to reach us since the Big Bang. These invisible structures could be generating gravitational waves that are pulling the galaxy clusters in their direction. While this remains speculative, it opens up the exciting possibility that our understanding of the universe's large-scale structure is still incomplete. Another exciting area of exploration is the potential link between dark flow and dark matter. Dark matter, which makes up roughly 27% of the universe's total mass energy content, is known to exert gravitational influence on galaxies and galaxy clusters. However, despite its presence, dark matter remains invisible, detectable only through its gravitational effects. Could dark flow be the result of an interaction between galaxy clusters and unseen concentrations of dark matter? Perhaps some large, invisible mass is causing these clusters to move in the way we observe. The gravitational pull of dark matter could be reaching beyond our observable universe, influencing the motion of these distant structures. Similarly, dark energy, the mysterious force thought to be responsible for the accelerated expansion of the universe, might also play a role in dark flow. Some researchers speculate that dark flow could be a manifestation of some interaction between dark energy and other forces beyond our observational reach. Could it be that the accelerated expansion of the universe is not happening uniformly, and that the motion of galaxy clusters toward this unknown point is an anomaly in this overall expansion? If dark energy is indeed causing this phenomenon, it would imply that there are features of dark energy that we are only just beginning to uncover. In exploring the implications of dark flow, it's also critical to address the possibility that this anomaly might not be related to any known force or structure at all. Could dark flow be an entirely new and unprecedented phenomenon? It's possible that what we are observing is a new form of motion, one that does not conform to our established understanding of gravity, dark matter, or dark energy. Such a revelation would be nothing short of revolutionary, opening up new avenues of research and leading to new theories of the cosmos. No matter which explanation ultimately proves to be correct, dark flow undeniably challenges our fundamental assumptions about the universe. It forces us to confront the possibility that we have barely scratched the surface in our exploration of the cosmos. As we continue to gather data and refine our methods of observation, we may discover even more anomalies that force us to reconsider what we know. The future of cosmology is filled with unanswered questions, and dark flow is just one of the many mysteries waiting to be solved. The study of dark flow, while incredibly exciting, is not just an academic pursuit, it's a reminder of how much we still have to learn about the universe. Each new mystery, like dark flow, opens a window into the vastness of space, inviting us to consider ideas that were once thought impossible. As science continues to evolve, so too will our understanding of the universe, and who knows what other cosmic anomalies await discovery. Perhaps dark flow is merely the beginning of a new chapter in our understanding of the universe, one that challenges everything we thought we knew. As we push the boundaries of science and technology, we will likely unlock even more mysteries that defy our current comprehension. Whether or not we ever fully solve the riddle of dark flow, the quest for answers will continue to inspire generations of scientists, philosophers, and curious minds to look up at the night sky and wonder about the secrets it holds. For now, we are left with the tantalizing possibility that something profound is occurring out there in the depths of space. The search for answers will take us to places we have yet to imagine, and no matter how far we go, the universe will always have more to reveal. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.